Ready? So, привет. That's my only Russian. Thanks so much for being in this workshop. I'm sad that I would like to, give this presentation in Russian, but I don't speak any Russian at all. So, apologizes for that. Um, I've been advised to try to. I usually speak very, very fast. I will try to go a little bit slower so that for people that speak English as a second language, they don't get lost. Better. Good. Um, I mean, while we are a bunch of people here, the idea is that, to the extent that is possible, the workshop is, as interactive as possible. So if while I'm explaining a topic, there's something that you disagree with, you have questions about it, I'm just going too fast, and you cannot, keep up with that, or there's something that I try to explain, and my explanation wasn't clear, just raise your hand, and ask your question or whatever. That's kind of like the idea for this. Um, well, this workshop is going to be about network reconnaissance for IPv6. I'm going, other than the explanations that that we're going to have during the workshop, there's quite a few examples of how to do things in practice. I have a tunnel connection for IPv6 here, so this network doesn't have a native IPv6 connectivity, but I established a tunnel. So if you are connected to this network and your machine is IPv6 enabled, you should be able to get an IPv6 address, and you should be able to have IPv6 connectivity. Before we get into the workshop itself, you should be able to try something like this. I mean, the network is kind of like terrible, but for some things, yeah, it's terrible. Well, we'll try to do our best. The tunnel apparently is working very, 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 very badly, but we have a few options to try, to make things work a little bit better during the workshop. Um, if the network is not, it's not fast enough, probably the practical exercises you're not going to be able to run them on the, on your own computers. For most of the exercises, I use tools that are available on Unix-like operating systems. For those of you that are using Windows and would like to try those tools, the conference has what is it, like an FTP site, a website, some place where they put like the virtual machines, like a Linux virtual machine that you can use to run the tools. Okay. But in any case, all the slides that obviously you will be able to get and download, they are full of pointers. So if you want to try, the tools or the examples while at home or whatever, you will be able to do that. Okay, so brief presentation about myself. I've been doing during the last few years a lot of work on IPv6 stuff. I'm the author of 30 IETF RFCs. I don't know if you know what RFCs are about, but they are the standards for internet protocols. Of those RFCs, about a little bit more than 10 are on IPv6. So I used to work on other areas like transport area operations and so on. But during the last few years, what I've been doing mostly has been IPv6. And quite some stuff of what I'm going to present here is stuff that I publish in some of those RFCs. I'm also the author of, I would say, one of the only 2 or 3 freely available toolkits to play with IPv6. This is one of the toolkits that we will be using during this workshop. Before actually getting on this stuff, I started to do security assessment of communications protocols for these 2 organizations. That's kind of like where I started to do this kind of stuff. For these people, I did work on other protocols, but essentially what I ended up doing was the same stuff that I did for them, but for other protocols. And I have a website, which is essentially kind of like, yeah. Duplicate display. What do you mean duplicate? To put it here too? Yeah. So while we get that fixed or we get that sorted out, um, in that website you essentially have pointers to RFCs that I wrote or articles. Most of them are on this topic. Why am I presenting on this topic? A while ago, I found this quote by Ken Thompson. You probably know this guy. And essentially, what the guy says is that at times when you have spent a lot of time working on some stuff, it's nice to present the stuff for other people to, let's say, analyze or, let's say, share their opinions, insights, or and so on. Um, well, in theory, if I'm giving this workshop, I'm supposed to know about the stuff that I'm, presenting. Please feel free if there's anything that I'm talking about that you disagree, raise your hand and ask the question. Uh, yeah, it's essentially impossible that you ask like questions that are more stupid than the ones that I have asked in the past. So don't worry about that a lot. So I guess I have to do this again, right? Um, wait, wait. No, no.
Dear friends, it's the PHDays 2017 here. It's the mid-time of
Because it's likely that if we, end up moving, it may not work at all. You know what I mean? So I would play safe in that case.
announcement about
Okay, so we're back. Um, if you were able to connect to the local network and everything is, working as expected, and if you were to do something like this,
you can see and even touch the cloud. There's like a control stand on the first floor. Delicious coffee and seminars, cloud
let's
security
see.
waiting for you. Don't skip it. Come to the web control stand for details. Thank you, web control, for supporting the forum.
This is an indication that you'd be using the tunnel that I set up for this network, okay? The connection is going a little bit slow, so if everyone starts using the tunnel, it could be the case that, it's going to be slow, but it's something.
Wish to talk further.
Okay, so we go back to the slides.
Serve refreshments.
I was saying that
We find
much of the stuff that I, yes,
central zone.
okay. Um, I was saying that much of the stuff that I'll be, presenting in this workshop is, stuff that I worked over the last few years. Um, even when, in theory, the person that is running the workshop is supposed to know about the stuff that, he's presenting, I'm always, happy to hear like comments, or if there's something that you disagree with what I'm saying, I mean, please speak up, because there's always the chance that I might learn something, from, the guys that are attending. Okay. Okay, introduction. So this presentation is about network reconnaissance, and I happened to look up the meaning of this word because it's so much used in the security field, and it turns out that apparently it's a word that is employed a lot in military circles, and it's essentially about observation of a region to locate an enemy or a certain strategic features. And when you use that phrase or that term for for networking stuff, it essentially means that we are going to locate or identify possible targets, and we are also going to learn information about the network that eventually we can use for performing attacks. Okay. So this presentation itself is not about performing the attacks, but it's actually about gaining information that you could subsequently use to perform the attacks, okay? So for people that might be expecting that I run exploits or that kind of stuff, this should be the moment to leave. Because at times people get very frustrated. They stay for an hour and they say, well, I mean, 2 hours and he didn't run any exploits. Well, there's not going to be any exploits. Okay, so this is the time to get frustrated. So essentially, what we're going to do is we're going to try to evaluate what's the kind of information that we can learn about an IPv6 network, and obviously we're going to stress on stuff that is different from the IPv4 world, okay? So obviously I assume that you know what a port scan is, what's an address scan, and so on. We are not covered that for the IPv4 world, but what I'm going to try to do is to try to show you what's different or what's new in IPv6. A couple of comments about network reconnaissance in IPv6. If you think about network reconnaissance in today's IPv4 world, most of it is about network address scanning, okay? So you go through a range of IPv6 addresses and you do a port scan or you do a pin sweep or something, but that's mostly what is network reconnaissance about, or at least the basic part of it. Now, IPv6 has rather substantial changes when it comes to addressing. Actually, IPv6 is all about the addresses. That's why the protocol has been developed. Among other things, it has a much larger address space. So in IPv4, you have 32 bits, but in IPv6, you have 128, which is much, much more. And also, there's another thing that, for people that are new to IPv6 and they come from the IPv4 world, in IPv6 it's quite usual that a single host, the same host, uses multiple IPv6 addresses for the same network interface, okay? So usually in IPv4, you look at the configuration of a network interface card and you always have a single address. For most cases, whether that's a private address, whether that's a public address, but a single address. In IPv6, the rule or the normal scenario is that every single network interface card has multiple IPv6 addresses. And those addresses are going to be have different properties. For example, they have different scopes, meaning some addresses are going to be like local or private versus other addresses that are going to be global. And they also have like different lifetimes. For example, some addresses are said to be temporary, that only last for a short period of time, whereas other addresses are permanent, or they are supposed to last almost forever. So the question is, how can we learn information about IPv6 networks? So the first and most obvious question is whether address scans are feasible in IPv6. So you are used to do address scans in IPv4, with Nmap or any tool that you use for scanning. Now the question is, can you really do address scans in IPv6? We're going to try to find out whether that's possible or not, or if it's possible, but to some extent, we're going to try to find out what has changed and what not. And then for scenarios for which address scanning is not possible, we will try to evaluate techniques to find, for example, possible targets. The approach for this presentation is, first of all, understand the theory. For me, the interesting part of this stuff, at least from my point of view, it's actually all the concepts behind the tools. The tools are just like a proof that the concepts actually work in practice. But I kind of hate when you have a presentation in which people are running so many scripts or tools without knowing what is going on behind that. So the idea of this presentation is to run fewer tools but understand better the ones that we are running, okay? And even if for some reason you don't like the tools that we are using, the idea is that you will know the concept so well that if you don't like these tools, you build your own, but you will have the knowledge to do that. So, brief introduction about IPv6. And I can make a very short comment why I introduced this. I kind of participate in two different communities. One is like the networking community, like IETF, where people develop standards for networking and so on. And yeah, some of them care about security, but not all of them. And in those environments, I would say virtually everyone knows what IPv6 is about. I mean, they know what it is, and to some extent, they know how the protocol works. Now, in my experience, when you move to the security field, that people are focusing on other stuff, you talk about IPv6 and a large number of people, they have heard about IPv6, but they don't really know what exactly it is, what's going on with IPv6. It's something that, it's a standard, but nobody uses, or is it something that is being deployed, or what? And also, at times, it's not clear to people, like, how does this protocol interact with, the existing IPv4 protocol? So, in this brief introduction, I will have like 5, 6, 7 slides, which are supposed to summarize everything, so that if you never heard about IPv6, and this is the first time that you're going to listen to something related to IPv6, you kind of like, get into speed to understand the rest of the presentation. So, the theory is that when it comes to the IP protocol, you need one address for each node that connects to the network. That's the theory, okay? Even so many years ago, it was clear that we were going to run out of IPv4 addresses. So we had these devices, NATs, which are probably one of the most successful technologies from some point of view, that were deployed in many, if not most, networks. Okay. So what do these devices do? Obviously, they allow you to share a single address that your ISP is giving to your home, for example, and they allow you to share that address with as many devices, kind of, as you want. Okay. When these devices, NATs, were introduced, like many, many years ago, more than 20 years ago, the idea was for these devices to, let's say, slow down the exhaustion of the IPv4 address space. They were not meant to, to give you the chance to share addresses within your network. That was a side effect. That wasn't really the intention. But the intention was that, by deploying these devices, we could slow down the rate at which we were going to run out of IPv4 addresses. But this was just, a technique to slow down the address exhaustion. This was not meant as like, the definitive or the long-term solution for the problem of running out of IPv4 addresses. When it comes to IPv4 address exhaustion, these are the current data and the projections for exhausting, the rest of the IPv4 address space. This guy, Geoff Houston, he works for an organization called APNIC. He does a lot of work on this stuff. So if you look for Geoff Houston address exhaustion, you will see pages and pages on what's the model that he used for this, blah, blah, blah. For me, what's most important about this graph is not when exactly we're going to run out of IPv4 addresses, but rather that it's quite clear that we're going to run out of addresses. Then we can argue whether that's going to be like 2017, 18, 19, 20, 25. It doesn't matter. But in terms of like, let's say at most 10 years, we're not going to have any more IPv4 addresses. So obviously, at that point in time, we will have to have a different plan to actually communicate over the internet. So what is IPv6 about? Essentially, it's a protocol meant to solve the problem of the depletion of the IPv4 address space. Essentially, IPv6 employs 120-bit addresses as opposed to the 32-bit addresses that are employed by IPv4. It provides exactly the same service as IPv4. The reason for which I stress this is that it's quite frequent that when you start reading, let's say, articles in magazines and so on, and you start reading about IPv6, you read about things like improved quality of service, improved security, improved something, well, which is not true at all. The only thing that IPv6 does is providing an increased address space. That's it. It doesn't have any improvements in any other area, okay? I mean, this is politically incorrect to say, but it's the truth. And another problem with IPv6 is that it's not backwards compatible with IPv4. So while the name would sound like, well, it's a new version of the same protocol, well, actually the protocol could have been named in any other way because it has nothing to do with IPv4. It's totally incompatible. There's no way in which you can make these two protocols, talk to each other. So the name of the protocol is similar to IPv4. The protocol has nothing to do with IPv4, okay? So this small graphic that I have in this slide tries to illustrate what happens as we deploy IPv6. On the left-hand side, you have like, well, in that network, there's a single host that only employs IPv4. Obviously, that node can only communicate with nodes that support IPv4. Then on the right-hand side, you have a node that speaks IPv6. Obviously, that node can only speak with nodes that talk IPv6. And in the middle, you have a node that is said to be dual stack node. Dual stack means that it supports both protocols, okay? It should be obvious that the node that is in the middle is able to talk to any of the two nodes. If it wants to talk with the node on the left, it's going to, employ IPv4. If it wants to talk with the node on the right, it's going to, employ IPv6. But in principle, there's no way in which the node on the left is able to talk with the node on the right. It's like, you can think of this as, people speaking languages. So the guy in the middle, let's say, speaks Russian and Spanish. The guy over there, Spanish, and the guy on this side speaks Russian. So the guy that speaks both languages speaks with any of them, but the other ones, they cannot talk to each other. Now, while this might seem simple and stupid, this is actually one of the main reasons for which IPv6 had and still has big problems with deployment, because it's not backwards compatible. So you are deploying a protocol that essentially cannot interoperate with the protocol that you're using for the internet. So you have to start from scratch. It's not that you can fall back to the old version of the protocol. It's a totally new protocol. Now, when the deployment protocols of IPv6 became, clear or evident, the IETF designed a few techniques to try to help, deploy IPv6. One of these techniques is what, we know as tunnels. So let's say that we have two different networks, the one on the left and the one on the right. This could be, for example, two faculty networks where the administrators have deployed IPv6, okay? Now, they are connected to the internet, but, their ISP only supports IPv4, okay? So in the network, they have IPv6 support. But in the middle of the two networks, the network that connects the two networks only supports IPv4. Now, obviously, if you want the nodes on the right to talk to the nodes on the left, you have to do some kind of magic in between. Obviously, the IPv6 packets cannot go through the main network because it only supports IPv4. Now, obviously, what tunnels do is essentially they, both tunnel endpoints, essentially encapsulate the IPv6 packets inside IPv4. They send the packets on the IPv4 network, and obviously the other tunnel endpoint is going to decapsulate the packet and send the native IPv6 packet on the other network, okay? So obviously the idea of, employing tunnels is that if you have IPv6 islands, that is networks that employ IPv6, and in the middle you have a network that doesn't support IPv6, well, this is ugly, this is not the best thing that you could do, but at least, it allows you to intercommunicate the two networks. Just to give you an example, if you were able to, for example, run ping, IPv6 ping to Google or any site on this network, the technique that I use to provide IPv6 connectivity on this network is a tunnel. So the local network doesn't support IPv6. So what one of my machines, virtual machines, is doing here is it announces an IPv6 network. So if you send packets to the IPv6 internet, they all come to my machine. They are sent inside IPv4 packets over the internet, and eventually they get to a tunnel endpoint like that one, where the packets are decapsulated and sent natively on the IPv6 internet. Obviously, as you could imagine, there are performance problems because it's an overlay network, so the round trip times are going to increase, blah, 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 blah. But, at times that's the best that you can get. And there's another technique, which is quite horrible, but again, at times that's the best that you can get. That, it's a technique meant to try to connect IPv6 only nodes with IPv4 only nodes. So I was saying before that when you have an IPv6 only network and an IPv4 only network, these two networks cannot talk to each other, and that's true. Now, if you deploy that box in the middle, which is actually, it's not really just a NAT, it's like a protocol translator, what that box over there tries to do is it takes an IPv6 packet and it creates a completely new packet, an IPv4 packet, to send to the IPv4 internet. Same thing happens the other way around. You get packets from the IPv4 internet, they get to the NAT, and they essentially throw away the original packet, and they create a new packet that now is IPv6. As you could imagine, since you are like creating new packets and completely discarding the previous packets, there are lots of features that are lost, for example, and there are lots of things that can go wrong, okay? You might ask, well, is anybody using this kind of thing? Well, the only scenarios that I know of in the real world where this kind of technique is employed is for some mobile operators. For example, it is known that in the United States, I think it was T-Mobile, they deploy to some clients only IPv6, okay? Obviously, the reason for that is that they want to support only a single protocol. It's, let's say, easier than supporting two protocols at the same time. But obviously, you know, for the typical user, if you give them IPv6, well, they can get to a few sites, but not to most of the sites, okay? Yeah, Google, Facebook, Yahoo, and a few others are dual stack. But if you look at this, let's say the top 1 million sites from Alexa, probably less than 5% of the sites are dual stack. So you really need IPv4. And if you want to deploy only IPv6, well, you need to do something like this to provide IPv4 connectivity to those IPv6 nodes. Now, so essentially what I explained so far was that the two protocols are incompatible with each other. If we have islands of IPv6 networks, we can employ tunnels to connect those islands. And if we want to make IPv4 nodes reachable from the IPv6 world, we might employ translators. Now, even after seeing that, you might wonder, well, I mean, that's totally fine, but let's say that I'm trying to visit, let's say, Google site. I mean, which protocol am I going to use? I mean, how does my browser decide, which protocol it employs, like whether that's P4 or that's P6? Well, in practice, what happens is something like this. The details vary from one implementation to another, so it doesn't need to be exactly like this, but the idea is true. Essentially, if you are on a node that is dual stack, that supports both protocols, and let's say you're trying to browse a website, let's say Google, your browser is going to try to get A records and quad A records from the DNS. The A records are the IPv4 addresses, okay? The quad A records are the IPv6 addresses. So essentially, your node, if it has both V4 and V6 connectivity, it tries to get both of them. And you might wonder, well, how does the node decide whether it should use IPv4 or IPv6? It depends. There have been implementations that they always prefer IPv6. There are implementations that only prefer IPv4. And there are implementations that, for example, they send the queries at the same time, and they use whatever they get first. Okay? Now, this might give you an idea that, all of this makes network troubleshooting quite harder. Why? Because now you try to browse a site, and, chances are that you might employ IPv4, and you find some kind of problem. Then you want to reproduce the problem and try to get to the same site. But just by chance, you end up using IPv6, and everything works fine. So this is not really nice at all, but this is what we have, okay? Okay. So current extent of affairs. So all of this is theory, essentially, right? So you might wonder, well, if I want to deploy V6 on my network, I mean, are there devices that support it? I mean, is anyone deploying V6? So most of the general purpose operating systems already support IPv6, whether that's Windows, Mac OS, Linux, or whatever that is. So they are prepared to get IPv6 connectivity. Obviously, what usually happens is that you connect to a network where there's no, let's say, DHCP server for IPv6, so you don't get an IPv6 address, okay? But your operating systems are prepared for that. Now, you might wonder about other devices, like CPEs or those, cheap little boxes that you use in your, home network that are provided by your ISP. Well, in many cases, those boxes, they do not support IPv6. And that's one of the main problems that some operators meaning to deploy IPv6 are having. Because let's say you have an installed base of, let's say, 20 million customers, and you want to deploy IPv6. Okay, 20 million customers. Let's say that each device is, let's say, €5. So you have to spend, what's like 100 million euros just to replace the boxes. So you end up saying, well, this IPv6 thing is actually quite expensive. So in theory, it's not expensive, but all these boxes I had to replace, so it gets like expensive. So that's one of the reasons for which in many places you don't see IPv6. there's also the case, I mean, there are ISPs that just, they didn't deploy IPv6. But there are also cases where the ISP supports IPv6, but maybe at home you are not getting an IPv6 connection because your CPE device doesn't support it, okay? So things are moving in that direction, but, things are not at the state that we'd like them to be. Deployment. IPv6 deployment was like totally ignored for so many years. If you go back, let's say 15 years, the support or the deployment that you have for IPv6 was almost zero, okay? What was the reason for that? Business case, money. You can be a technical guy that, works in the networking department of a company, and you go and ask your boss, well, I need this money to deploy IPv6. Well, how much money are we going to make for that? Well, nothing. No, then you don't deploy it, okay? There have been a few things that... Yeah. Oh, sorry. That happened in the, last 10 years or so to try to, change this situation. Among the most important ones were two, let's call them awareness activity. One was the World IPv6 Day, and the other one was World IPv6 Launch Day. If I recall correctly, the first one was June the 6th in 2011. The other one was the same day, but in 2012. The first event, World IPv6 Day, what happened during that day was that major content providers, Google, Facebook, Yahoo, and so on, they enabled IPv6 for a single day, just one day, to try to see what happened, okay? And obviously the idea after that, the idea was to gain experience, like real-world experience with the protocol, and 1 year later, during the World IPv6 Launch Day, these content providers essentially enable IPv6 for once and for all. So right now, for example, if you had IPv6 connectivity, you could, let's say, visit Yahoo, Facebook, or Google with IPv6 rather than IPv4 if you wanted. This is the IPv6 usage as measured by Google, okay? So it says that they get 20% of traffic of IPv6. In the next slide, there is a pointer, because it's quite likely that you look at that number and you say, well, that cannot be true, okay? Well, first of all, that's a number that is just measured by Google, okay? But if you go and look at, that URL, and if you cannot see it because of this thing over here, I mean, it will be in the slides that you will get, you can look at the stats, and you can also get the stats for specific countries. I didn't check the stats for Russia, but you could check, whether the, what's the level of IPv6 traffic that they are seeing. Then that's kind of like the background for IPv6. Now you might, wonder, well, why should I bother about IPv6? Why should I care about IPv6? Well, as I said before, most of the general purpose operating systems, they support IPv6 already, and there are increasing, deployments of IPv6. There are many countries, for example, in Europe. I can think of, Belgium, Germany, what else? Switzerland. I think there was Romania too, and a few others that have a quite, let's say, large amount of IPv6 traffic. Okay, that's something that is, happening, and at least when it comes to, let's say, popular sites like popular websites, most of those, popular websites, they are dual stack already. One thing that is quite interesting is that, let's say that you are, let's say, the security or the network administrator of some network, and you say, well, why should I care about IPv6 security? I mean, V6 is disabled on my network, so I don't need to care. Well, truth is that unless you do something in every single device on your network, those devices will still have support for IPv6. So as long as, or as soon as a node that has the ability to enable that V6 connectivity connects to your network, well, now the attacker is playing with something that you are not even, let's say, aware of. I don't know if you, this is a nice data point, but something like, what was it, like 10 years ago, there was a remotely exploitable bug in OpenBSD, one of the only few ones that were found, or that were publicly released, at least, that I think it was the last one, and that one involved sending IPv6 packets. Now, just imagine this. You have the OpenBSD box connected to a network. Let's say that someone tried to hack that box, and with IPv4 they can't. Now, some guy connects to the network, And even when you're not using IPv6, he's able to hack your box because your box is still receiving and processing IPv6 packets. Okay? So the moral of the story is that if you're really going to take the attitude of, I don't use IPv6, so I don't need to care about this, well, make sure you don't use IPv6. Really block it, and really make sure you block it in a number of places. Like, for example, at layer 2, like in the switches. Don't let the packets, Ethernet packets, go through the switch that are carrying like IPv6 packets. Another thing that is quite interesting, I don't have pointers here, but there have been at least 2 papers on this topic. There were some guys that they did this. Let's say that they found the 100 most popular sites from Alexa, and they obtained the IPv4 addresses and the IPv6 addresses for those sites. And they did the port scan on IPv6 and on IPv4. What you would expect is that you get the same ports open on each protocol, okay? Because at the end of the day, you don't care what's the internet layer protocol that you're using. If a server is, is a web server, well, it should have, let's say, port 80 open on both B4 and B6. If it's not open on B6, there's no reason that it should be open on B4. Well, what these people found was that that's not actually the case. When you look at, real internet servers, you find that, they don't have parity in the security policies that they employ. So some ports might be, for example, closed on IPv4, but they might be open on IPv6. So that's one reason why you might care about this. Because you might say, well, as long as I can use IPv4 for hacking, why should I care about B6? Well, maybe one of the reasons is that if you may be trying something that in IPv4 is blocked, but in IPv6 is not. And the last part of the introduction to B6 is an extremely brief comparison of the 2 protocols. So this slide essentially tries to summarize what's the same and what's different between the 2 protocols. Usually when one of the things that I do a lot is, providing IPv6 training. And one thing that you see a lot for people doing B6 training is that they take the attitude of, well, this is a new protocol, so forget about everything that you know from the IPv4 wall, and you have to learn from scratch. I'm a lazy guy in that sense, so my take or my viewpoint is that I try to make you reuse as much of your IPv4 knowledge as possible. So that's why, during the workshop and also in these slides, I will be always comparing to, how things are in IPv4. So that if you understand the topic, in IPv4, you can migrate those ideas to IPv6. So first topic over there is addressing. 32 bits in IPv4, 128 bits in IPv6. That's the most important difference here, the most important one. Second one is which protocol IPv4 and IPv6 employ for address resolution. Address resolution is obviously you map an IP address into a link layer address. In IPv4, it's called ARP. Everyone knows about that. In IPv6, it's called neighbor discovery. Essentially, rather than using ARP packets, you use some ICMP packets. Okay? The details, they don't matter that much. But just it's a different protocol to do exactly the same thing. Third line over here, auto-configuration. In IPv4, in theory, you can have DHCP and configuration with ICMP messages. In practice, you only use DHCP. In IPv6, you have 2 main protocols for auto-configuration. One is DHCP version 6, which is analogous to, DHCP version 4. But you also have something that is called SLAC, or stateless auto-configuration, that employs ICMP messages. It's quite simple. I mean, the name sounds funny, but it's quite simple. You connect to a network, and there's a local router that is sending network configuration information as broadcasts with ICMP messages. So your node receives that information, and then it configures everything that it needs to configure, okay? The other one is fault isolation. Fault isolation is essentially reporting network problems. Well, essentially in B4 and B6, both of them, they employ ICMP. The protocol is different. There's a different version of the protocol, but they are essentially the same. It's just the packet format that changes. IPsec support is optional in both protocols. You might wonder why I mentioned this. Well, one of the reasons for which many people for so many years said that IPv6 was more secure than IPv4 was because at some point in time, the protocol specifications said that if you were employing IPv6, you had to have an IPsec implementation, okay? So it was mandatory to have an IPsec implementation in every node that supported IPv6. Now, that was just words on paper. I mean, nobody cared about that, to such an extent that eventually the IETF, the people that standardizes the protocol, essentially they say, well, if nobody is complying with our rules, then let's change the rules, okay? And that's actually what happened. So IPsec is optional in the two protocols. Sorry? Neighbor discovery poisoning attack, same thing. You just use different packets. So his question was, in IPv4 I have R poisoning attacks. Do you have something similar in V6? Yes. Neighbor discovery poisoning attacks. In a sense, it's so frustrating because you would expect that something that was solved in IPv4 is not present in IPv6. Well, exactly the same stuff. If you want another example that is not in the slides, but in case you wonder, in IPv4 we used to have source routing. Remember about the 90s, right? Well, IPv6 had a routing header that essentially implemented the same functionality. Same thing. Another example, you might remember the ping of death in the 90s, a single packet that could crash your system. Well, Microsoft re-implemented that for IPv6 too. So, yeah. The last item over here is fragmentation. In the IPv4 world, packets can be fragmented by the end systems, like your host, or by the network. If you send a packet that is too large, some router in the middle can fragment the packet into smaller pieces. Now, in IPv6, fragmentation can only happen at the end host. That means that somehow every system that connects to the network has two options. Send the packets small enough so that you know that they don't have to be fragmented, or option two, somehow you discover what's the maximum packet size that you can use in the network, okay? Those are essentially the difference between the two protocols. In most of the cases, like his question, if you can think of something like some vulnerability that you remember from the IPv4 world, it's quite possible that you can migrate the same stuff to IPv6. Well, so he's asking about broadcast. Well, in IPv4, you had you could send, let's say, broadcast to a remote network. That has been removed let's say that has been removed from IPv6. Okay, you do have broadcasts on the local network, but those are broadcasts that you can only send on the local network, but not to a remote network. Okay? Yes. Yeah. You could say that. That could be an improvement. Yeah. This is the header format of both of the packets. The fields, they don't matter that much, but if you take a look and try to compare the two packets, essentially there have been 1, 2, 3, 4 fields that have completely disappeared. Okay. Among those fields are all of the fields here that are employed for fragmentation. Sorry, these ones are not present here. So you can see that there's no identification, no fragment offset, no flags, no nothing. Why? Because in IPv6, if you want to fragment, rather than having that supported in the fixed header, you have to add like an option to the packet. So what they try to do is, in the base header, only keep those fields that you are supposed to be employing always, okay? Now, since fragmentation is, you don't necessarily need to use fragmentation all the time, that's why it has been removed from the base header. Now, there's another field that has been removed, which is the header checksum, okay? Now, I was told that I have t-shirts, and I have to get rid, and I'm going to forget. So, if you want the first t-shirt, now the question is, why do you think that the header checksum has been removed from V4 to V6? Well, I mean, there's some truth to it, but so what he's saying is it's not useful, okay? Well, actually, I mean, there are protocols that re-implement checksums, okay? And you could have easily, if you wanted, like a protocol that doesn't employ checksums. So you might need them. Actually, the reason for which the checksum was removed was more, let's say, economical, if you want. Yeah. No. No. So this one is going to be pending for next question, okay? So what was the reason for the checksum? If you have to compute a checksum in the packet, every time that you get a packet, you have to recompute the checksum, okay? Now, if you're a router manufacturer and you want your devices to go fast, you improve your hardware and then you start lying. So you say, well, I mean, what's the stuff that I'm computing that, at the end of the day, if I don't compute, nobody cares? Checksum. Now, everyone was lying about that. So eventually people developing the protocols, well, if nobody's computing the checksum, so let's stop with this joke and let's remove the checksum. If at the end of the day we have the checksum but nobody computes it, okay? It's not that it's not useful. So if you just look at the IPv6 packet, you might get a packet directed to you that was actually directed to somebody else. But there was an error in the header that you were not able to detect, okay? Yes, there are protocols like, if you look at TCP, it has a pseudo header that could detect that, but that's not very nice, this nice protocol design, you could say. In IPv4, he's asking how you employ the checksum on before. You compute the checksum over the IPv4 header. So if there's something that changes on the IPv4 header, the checksum is going to fail. So the idea with the IPv4 checksum is this one. If you get an IPv4 packet, before doing anything with that packet, you are supposed to check the checksum. Why? Because if the checksum failed, that means that there was an error in the packet. And if there was an error, chances are that maybe the error was in the destination address. So maybe you're getting a packet not because it was actually sent to you, but because the destination address was corrupted, and that's why you received the packet. Yeah, but not only, I understand what you mean. One of the problems that we have when you look at the internet protocols is that the design is not really clean. For example, you say, well, I have a checksum in layer 2 and I have a checksum in layer 4, but actually the idea of layering is that the layers are independent. Now, yeah, you have a checksum in Ethernet, but what if you are using like a serial line? Why should you use Ethernet? Okay, so, and this is the general packet format for IPv6. I mean, the letters are small, but, the idea is, it's quite simple. This is the base IPv6 header, the ones that we were looking at at the previous slide. These are what are called extension headers. One extension header, the other extension header, and then you get the payload, okay? If you took like computer science classes, this is like a linked list, okay? So you have one node here, this is the first header, then you insert an optional header, another optional header, and then you get the payload. In order to get here, you need to jump from one header to another. There's nothing like, let's say, a payload offset or something like that. So if you want to get here, if you want to find what the payload is, you have to jump and process all of the extension headers, okay? The idea is that if you are not employing any options, these two header fields here won't be present, and you will just have the payload following the base IPv6 header, okay? Let's give it another try. What's the, let's call that improvement of this format as opposed to the IPv4 format? No. Well, I mean, the base header you could say is smaller size, but not really. I mean, another one. So what do you think is the improvement of this? More than that. Let's say I'm going to take that for valid. The thing is, with this structure, you have much more space for options. In IPv4, the space that you have for options was variable length, okay? But it had a limit, like 40 bytes. Now with this, you can use as many bytes as you want. Like this could be like 500 bytes if you want. And then you can add another header that is another 500 bytes. So you have more, if you want, flexibility for options. I mean, that's the theory, right? So that's kind of like the background for, IPv6. Let's see where we are. Okay. So now let's talk a little bit about tools. During this workshop, we're going to use two set of tools mainly, okay? First one is the toolkit that I authored myself. Second one is THC IPv6. You probably know about it. That's the very first toolkit that was ever released about IPv6. I think besides the features, I think that the most important contribution, which is great, is that this guy, Van Hauser, or Mark Oise from Germany, he, essentially published the first set of tools that you could employ to actually play with the protocol. And then for some stuff, we're going to use Nmap, okay? Let's briefly look at, each of these toolkits before actually looking at specific tools. THC, as I said before, was for a long time the first and only toolkit for playing with IPv6. The idea with THC is that it's extremely easy to use. It's like, for example, you have a tool that is a scanner, and you just put the name of, let's say, the network or the interface, and you get what you expect, like a list of systems. And you have another tool that is called DOS, blah, 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 and if you just run the tool with the target, that system crashes. You don't know why, but it crashes, okay? So the idea, I don't know if it was like a design decision, but when you look at the tools of this toolkit, essentially they are tools that, implement specific attacks. And these tools make it very easy for you to exploit those attacks. But they are not flexible, okay? So if what you want to do is available here, it's going to be very easy to implement it. Now, if what you want to do is not available in one of these tools, it's going to be quite hard for you to use this toolkit to use what you want to do. Other features, well, it's free software and only runs on Linux with Ethernet, okay? So if you are using, let's say, macOS, I don't know if there's a way to actually make this work over there, but at least in principle, it's not supposed to work, okay? And this is the homepage for THC IPv6. This one is already, I don't know, I don't remember if with this exact name, but if you search for THC IPv6 and you use, let's say, Debian, it's even available in the package system. And this is the Git repository, which is probably even better, because you are going to get the most up-to-date version of the toolkit. Then there is the second one. This toolkit was produced like more than 7 years ago, while I was doing some work for some people in the United Kingdom, okay? Now, this toolkit was never meant to be public. And I was once, years ago, teaching an IPv6 security course, and I talked about this toolkit, and one of the attendees said, well, but the toolkit is publicly available. I said, well, no, that's not possible. And they said, yeah, it's publicly available. So eventually, the guy showed me a link, and the toolkit was publicly available. Now, the funny part was that it's not that there was some kind of like leak, but rather that there was, at the time we were disclosing this toolkit, but to specific companies, universities, and so on, there was some guy that got the toolkit and said, oh, this is useful, and he posted it online. And, after that, it became already public, which from some point of view is not nice. From another point of view, that's what allowed me to continue with the development of the toolkit, because the toolkit had already been released, so there was no problem with continuing the evolution of the toolkit. What are the goals of the toolkit? First of all, it's meant to be extremely flexible. So the idea is that it contains a lot of tools, and essentially, if there is let's say, there's a tool for ICMP version 6, it's quite possible that whatever you want to do with ICMP version 6, you can do it with that tool. Now that comes at the price, so it's not that easy to use. So quite a few times I talk to people and they say, I don't like your toolkit. I use THC. Why? Because I run the tools and they do nothing. Well, yeah, I mean, if you run the tools and you don't know which parameters you have to set, you don't get anything. I mean, for most of the tools, it's like that. You have to know what you're doing, except for one or two tools, okay? The other thing is that it's supposed to be clean, portable, and secure to the extent that is possible, okay? Portable was kind of like an experiment for myself, let's say a disgusting experiment for myself, because at times there's stuff that is supposed to be easy to do in different operating systems, but ends up being extremely painful. Like if you are into programming, like using pickup at the low level, it's a nightmare. If you want to do something other than you just capturing a packet and printing it on the screen. So many things are like quite painful. What else? And then to the extent that is possible, I try to, implement it in a safe way. Like, when it comes to details, like release privileges that you don't need anymore. Like I was kind of like surprised when I was digging into, popular tools that you normally use for security, and they are security tools, but they run as root for the whole lifetime. Probably they just needed, super user privileges for opening some kind of descriptor. But even then, they don't release those privileges. So you will see some of this stuff. So even if at times the code is buggy, usually the tools have released all the privileges, so they cannot do much. They have good documentation. There's a reason for that. I mean, certainly that wasn't funny, but we were sending these tools to companies like big vendors, and the people that we were sending the tools to were not the same people using the tools. So we had to give them information about everything. So there was a lot of work and a lot of pain in producing manual pages for the tools. A lot of work. Supported operating systems, virtually most of the popular BSDs, Linux, macOS, and OpenSolaris, okay? macOS, I never used macOS, never in my life, or probably only once. So at times there's people that have a macOS, I send them the code, they try it, and that's the way that I develop the code for macOS. License JPL, this is the homepage, and this is the Git repository for that, okay? This is what I was explaining before about this toolkit. The idea of the tools in this toolkit is that if you know the protocols, it's easy to apply your ideas to the network. If you know what you want to send, it's easy to do it. But the part on the left is required. If the part on the left is not there, the tools are not going to be of any use. Nmap. Well, there's not much to say about Nmap, okay? But I will do like a brief description of what's the IPv6 support in Nmap. Obviously, I assume that everyone knows Nmap, or you should know Nmap. Well, first of all, when it comes to address scanning, for a long time, they didn't even support like scanning ranges of addresses, okay? So you could port scan a single IPv6 address, but you couldn't scan a network for available nodes. I don't know in which version, let's say in the last few years, they did incorporate support for prefix scanning. So you specify a / something, and they will try all of the addresses in that prefix, okay? Whether that's useful or not, that's a different question, but they do implement this. They implement local techniques for local network scans. We will, discuss these techniques later. They have some IPv6 specific techniques for host scanning. They have full support for IPv6 port scans. So everything, or I guess virtually everything that you can do in IPv4 when it comes to port scans, you can do it on IPv6 too. And they even have operating system version detection. But, let's say the granularity, it's nowhere near what they have for IPv4. I mean, for IPv4, it's insane. They can even distinguish, different kernel versions and blah, blah, blah. With IPv6, it's way more coarse. It's like, well, it's some BSD or it's something like that. But, I mean, it's still awesome. OK, so so far, this was kind of like the introduction to v6. Are there any questions so far? Something that wasn't clear? OK. So first topic that we're going to discuss, and this is like the main topic, is the IPv6 addressing architecture. While obviously there are things that change in IPv6, like packet formats and all of that, let's say the biggest difference or the most important difference is, has to do with, addressing. And as I said before, IPv6 addressing, or the larger address space, is the reason for which people deploy this protocol. People don't deploy IPv6 for security. They don't deploy IPv6 for quality of service. They just deploy IPv6 because they need more addresses, and they don't have more addresses with IPv4. That's it. Brief overview. Main driver for B6 deployment is increased address space. B6 employs 128 bits addresses. Other than that, things are very similar between B6 and B4. For example, obviously you will have a routing table in IPv6, and you will see that the addresses are aggregated into prefixes. So when you look at the routing table will say, if you want to get to this network, you should use this gateway. If you want to get to this node, you should use that gateway, and so on. Second, there are different address types, okay? Unicast, anycast, and multicast. That's the same thing as in IPv4. The only thing that you don't have in B6 is like broadcast, but the rest is the same. And then, third one, there are 3 different address scopes. You have a second chance for the t-shirt. So, can you tell me an example of global address, link local address, and let's say just local address? Huh? Well, global is an internet address, but what about link local? N- What do you mean by automatic address? You got it. So in IPv4, if you connect to a network and there's no DHCP server there, some operating systems configure an address. If I remember, he said 169, which is an address that is auto-configured. They say, I connect to a network. There's no DHCP server, so I have 2 options. I get no address, and I can talk to nobody. Or option 2, I auto-configure an address that I know is not going to be global, but at least I can use on the local network. So, for example, you could use that for, like, the what's called like network neighborhood in Windows, what's called Bonjour in let's say Apple products, or Bonjour, or what's called multicast DNS. So you can employ that address for communication on the local link. IPv6 has the same thing. Obviously, the numbers are going to be different, okay? But the concept is exactly the same. Now, this is probably the only difference between the 2 protocols, and at times people get surprised about this. In IPv4, no matter whether the address that you configure is an auto-configured address, a private address, 192, blah, 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 or a global address, typically you only get one of those. Global or private or link local. But you don't get like 5 different addresses for the same interface. Now, in IPv6, you configure at least 2 addresses. One address that is link local and an address that is global if you are connected to the internet. And actually, in practice, you might even configure more addresses. Like, for example, it's quite usual that you have, let's say, a link local address. And then when it comes to the global addresses, you configure 2 types of addresses. One address that is called stable. That address remains the same for the whole lifetime that system remains connected to the network. And some systems also configure temporary addresses, which, as the name implies, they change over time. They are supposed to be good for privacy. So even when you stay connected to the same network, you have an address that is changing all the time. So you connect to one side, then you connect to another, and you look like 2 different systems, in theory, right? Then things are not exactly like that. So this is something that at times, people get surprised. Like, you connected to an IPv6 network, now you get like, maybe 5 addresses. Why do I need so many? Okay? I don't know if how things are working here. PP. So this is my system. You can see this is a link local address. Obviously, the reason for which I'm able to identify that because all link locals start with FE80, okay? These two addresses over here, I don't know why I have two, they could be, so this one looks like a stable address, this one looks like a temporary address. I should check. But at the end of the day, it doesn't matter. The important part here is that for the same prefix, or not same prefix, you had two prefixes here, you got more than one public address, okay? So that's going to be the rule always. You look at the network configuration of an interface in IPv6, and you're likely going to see many addresses. That's the rule for v6. Well, I mean, let's put things this way. Let's say that we are connected to a network, and that network has two different connections to the internet. So one router will get you an address from some prefix. The other router will get you an address from the other prefix. Now, obviously, that's nice, but then it's your problem what you use. Now, you have so many addresses that whenever you have to send a packet, it's like, well, what's the best address that I should be using? You know? At times, it's problematic, I should say. There's even a standard, I think it's something like 30 pages, about how you should decide which address to use, okay? Because it's not simple. Like, let's say I have these two addresses. Maybe I want to communicate with some system. I use this one, and my packets get filtered. And I should have used the other one. But I have no way to tell that, okay? So, you know, at times, all the flexibility comes at the expense of complexity that is hard to troubleshoot. Okay. So, I was saying that IPv6 has 128 bits addresses, okay? Now, that obviously has implications. Like, if you think about the way in which we typically do IPv4 address scans, they are essentially brute force scans. You know that there is a /24 network that you want to attack, and you just scan the whole, the whole 8 bits for, that network. I mean, at the end of the day, the search space, the number of potential nodes that you have in that network is so small that it doesn't make any sense to try to use your brain and say, well, how could I possibly reduce the number of packets? You probably have even seen that there have been at least 2, 3, 5 studies published with results about scanning the whole IPv4 internet, okay? So if people could scan the whole IPv4 internet in terms of a couple of weeks, obviously scanning just a /24/16, it's easily doable. Now, 16, when it comes to 8 bits for the address or 16 bits for the host address, that's not bad. But if you think about 128 bits addresses, well, doing a brute force scan, it would take a long time, okay? And long time, we are talking about like hundreds of years. We're probably all going to be deaf by the time that you finish the scan. There are other things, like for example, when I was showing the configuration of my computer, like 1 minute ago, I told you, well, this one is a link local address. This other one is a global address. This other one could be a temporary address. Now, that's something new that wasn't present in IPv4. Why? Because in IPv4, you just have a single address for each node. So if there's a single address, whatever you want to do with that node, you have to use that address. You don't have choices. Now, with v6, maybe for the same node, you have 4 different addresses. Now, which one do you use? Like, do you try all of them, just in case, one is useful and the other ones are not? Do you instead try to, analyze the addresses and, discard the ones that for some reason are not useful? Well, that's something that is new in IPv6. These here, the different kinds of addresses, whether they are temporary, stable, link local, private, and blah, 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 coupled with the fact that every node has so many addresses, and the fact that the addresses are so large, so long to, to write down, essentially also means that you need tools to actually be able to work with those addresses, to easily filter, given a list of addresses, easily filtering what are the addresses that you want. Like, for example, if I have a file with 1,000,000 addresses, I could say, well, I want to discard all the multicast addresses because, I'm going to use these addresses for sending TCP packets. So multicast for TCP doesn't make any sense at all. So I want to discard all the multicast addresses. Now, if I'm trying to do something with a site that is, in a remote network, there's no point in using link local addresses. The packets are not going to get there, okay? So that gives you an idea that given a set of addresses, you typically have the need to actually process that addresses, like, for example, for filtering. Before getting into concrete examples about addresses, let's briefly summarize how IPv6 addresses are written down. I said before that IPv6 addresses are 128-bit long. If we try to write the IPv6 addresses in the same way we write the IPv4 ones, they would take us, like half a page. So what was decided to write down IPv6 addresses was to write them down like this, where each X is a 4-digit hexadecimal number, okay? So each X here is 4 hexadecimal, it's a 4-digit hexadecimal number. Now, there can be cases where you might have some number over there, some numbers over here, and in the middle, the address is full of zeros, okay? So maybe many of those numbers in there you just don't use at all. If you look at the relevant standard, they have like a way to compress IPv6 addresses, which is by adding this double colon, okay? If you find an address where you have a double colon, this means you should put here as many zeros as possible to make the address 128-bit long, okay? This means in this part, you should complete with as many zeros as possible so that the address is 128-bit long. Let's look at these addresses. For example, is the first one and the second address, the same or not? And why? So first one and the second one, they are the same. So functionally speaking, they are the same thing. It's the same thing written in a different way. Why? If you look at this second address in here, it contains the double colon, okay? Double colon means put there as many zeros as needed to make the address, 128 bits long. Zeros that are to the left of a meaningful number can be removed. So for example, what you have here is this 0 was removed because it's not needed. Same thing here. Now, all of these zeros in here are compressed with this notation, okay? And then the prefix in there is the same. What about the second one? Is it the same thing as the other ones or not? Yes, it is the same thing. So the only difference is that the difference between this one and this one is that all these zeros were written in the full way. Rather than just use a single digit, we use 4 digits, okay? What about this one? Same thing. Well, there's only, let me tell you another example. So one specific example that I have to note in this case, which was described in the previous slide, but I kind of like skipped it, is this one. The standard says that there's a special way in which you can write down an IPv6 address, which is by embedding, like putting inside the v6 address, an IPv4 address. What happens with this number, which obviously looks like an IPv4 address, is that each byte, this byte is encoded here. The second one is encoded here. You see? So this IPv4 address that you are putting in the left-hand side is encoded in the low order 32 bits of the IPv6 address. So to say it in a different way, this, at the end of the day, is the same thing as this, and as this, okay? Now, the moral of the story here is that there's only one, I don't remember, well, this one is the only one that is different. It's not the same thing. And you could easily tell, right? An A followed by another A. So this is clear, not the same as this stuff. All of the other addresses are exactly the same. Now, that should already, teach you something, that if you want to compare IPv6 addresses as text, well, you have to do something, because addresses that are, from a minimum, like let's say a semantic point of view, the same thing, they look different as text. So there's something that is called the canonic form of an address. Canonic form is like the smallest way in which you can compress an address, so to speak. Okay? So in this case, it would be this notation over here, where you have removed the zeros that are on the left and you have compressed the old zeros. There is a tool that is included in one of the toolkits, in the one that I produce, that essentially prints on the screen the canonic form of an address. Okay? I think I have some example. Let's say. So this is a text file that contains all the examples that we had in the screen before, okay? All these addresses in here. Now what I can do is, pipe all of those addresses to the address 6 tool. And what the tool does, it prints the canonic form of each of those addresses. So for the first address, it remains the same because it was in canonic form already. Now, if you look at each of the addresses, except for the one that is totally different, all of them look the same. What's the idea here? If somehow you have a text file full of IPv6 addresses, and you want to compare those addresses as text, first of all, you have to convert each address to its canonic form. Otherwise, you might do a text comparison that fails, but the addresses might still be the equivalent. It's just the same thing written in a different way. This is something, for example, that well, actually, before you could have something like that. You could have like leading zeros. I think that's still allowed. But in IPv6, it's quite worse. So this is what I just did. I had the addresses in a text file. This is the tool. -I means that it takes the it takes the arguments from standard input, and -c is to print the canonic version of the addresses. Okay. So what we have just seen is it's something that has to do with the address notation itself. We didn't even start to send packets. It's just because there are so many different ways in which you can write the same address, it's problematic when you want to compare addresses as text. So now let's take a look. Let's take a deeper look at the addressing architecture and the different address types. So this slide tries to summarize how you can possibly identify. This looks horrible. How you can possibly identify different address types. Like for example, colon 1. You see, colon and 1. That's loopback. That's the equivalent of 127.0.0.1 in IPv4. If I go to the console, this is sending a ping to myself. Same thing as loopback in IPv4, but just the address that we use here is different. What else? Multicast addresses, they all start with FF. Then we have link local addresses. All of them start with FE80. Okay? So that's when in one of the previous slides, when I was looking at the configuration of my interface, I said, well, this one is a link local. Why? Because it starts with FE80. Unique local unicast addresses, these ones, are the equivalent to the IPv4 private space, like the 192 blah, blah, blah. Okay? And everything else is global. So we go into a little bit more detail here. You might wonder, well, why let's say, if I have a network interface card and it configures many of these addresses, why should I use one address or not the other? Well, generally speaking, if you want to communicate with let's say, with the public network, with the global internet, you would employ global addresses, okay? Now, there could be scenarios in which it might make sense to use addresses with a smaller scope, like private addresses. Let's see if you can figure out one example. Can you think of, let's say I have a home network, okay? Usually, if you're using IPv6, which has, global addresses available for everyone, you could say, well, I want to give each of my nodes in my network a global address, okay? And I could always use those global addresses because they are useful for everything. I can communicate on the local network, I can communicate with the internet, and so on. What do you think would be a scenario in which it would be a better option to use like a private address, like the private address space? One? That's one option. So what he says is for security, and that's true. If the addresses have smaller scope, that by itself has an implicit filtering policy. Because if you are outside of the scope of the address, obviously you cannot get there. Like, the equivalent would be like if you have a network that employs, a remote network that employs 192 blah, 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 it's quite unlikely that you will be able to do something unless you are directly connected to that network. Now, there's a different reason. There's another reason that has to do with resiliency. What happens if I'm using global addresses for my network and I lose communication with my ISP? So when you connect to your ISP is leasing you the IPv something, IPv4, IPv6 addresses. Now, if the connectivity is interrupted, all your addresses are gone. And if the only addresses that you use are global addresses, just because you lost connectivity with your ISP, now you cannot communicate with any other system in the network. I mean, you could use link local, but let's say if your network has multiple network segments, you're dead. Because the only addresses that you have left are the link locals, okay? Now, if you were using private address space, the private address space doesn't need to be leased by anyone. So the communication with the ISP can get lost, and you can still continue using the same addresses. So it's not just security, it's also resiliency. It's like you lose communication with your ISP, well, you still have an address space that you can, do with it whatever you want. You might just have a network that never communicates to the public internet, okay? So that's one reason for which that might be useful. What else? Well, link locals, for the most part, obviously, as the name implies, they are employed to just communicate on the local network segment. And I would say that in most cases, they are employed for like security reasons. Like, for example, just to give you an idea, in IPv4, when you want to map an IP address into a link layer address, you use ARP, okay? ARP is a layer 2 protocol. You cannot route ARP packets. They don't go past routers. Okay, they die in the same network segment. Now, IPv6 employs ICMP packets for address resolution. ICMP packets can actually get routed, okay? So unless you do something in there, you could do like an ARP poisoning attack from a remote network because you can send the ARP packets to a remote network. So while it's not discussed here, there are two things that are done in the protocol to prevent those attacks. First one is to use link local addresses. So if you are not in the same local link, you are not going to be able to send those packets to a remote network. Another thing that is done, but for that specific protocol, is that the TTL, which in IPv6 is called hop limit, is set to the maximum value, which is 255. And for the case of neighbor discovery, which is the equivalent to ARP, if you receive an ARP packet and the hop limit, the TTL, is different from 255, you discard the packet. Why? Because if the hop limit is different from 255, that means that the packet went through some kind of router. And for a protocol such as ARP, that's not supposed to happen. So let's start about the format or the syntax of each of these addresses. This is the format or syntax of a global unicast address. These are the addresses that you should be employing when you are communicating with a remote system. Is there anything different between this address and a global IPv4 address? Is there something that you say, okay, well, this is totally different? Huh? Well, the only real thing that is different from IPv4, besides the size of the address, obviously, these are much larger, is that this part of the address in IPv6 is called interface ID, but in IPv4 is usually called host ID. Actually, host ID is not the proper name because in IPv4, the addresses never identify a node, they identify a network interface. Obviously, if you have two network cards, they get different addresses, so they cannot possibly identify the host, they identify the interface. So in V6, the name was corrected. So now this is called interface ID, but it's what you know as host ID in IPv4. Now, if you look at this, it's the same thing as in IPv4, just larger, okay? So you have a global routing prefix, which is the prefix that your ISP is listening you. You have some bits for subnetting, same thing that you do in, IPv4. And finally, you have some bits from which you choose different addresses for different nodes. That's no different from the IPv4 world. Now, the only difference, to some extent, is that this part is 64 bits. 64. In IPv4, not even the whole IPv4 address is 64 bits. Now, when you give humans so many bits, and they know they have lots of spare time, what they do, they come up with different things to do, right? You have nothing to do, you have so many options. So there are different things or different ways, different algorithms that you can use to select this interface ID. First of all, something that I didn't mention. Let's say the most common way in which you configure addresses in IPv6 is called stateless address auto-configuration. Translated to English or Russian, if you want, that means that you connect to a network, the local router tells you what's the prefix that you should use, but this part you select by yourself. Okay? So the router just tells you what's the prefix that needs to be employed for the local network. But it's you that decides what's the number that you use for the host ID. Obviously, there are two things here. First of all, this is so large, 64 bits, that the chances of two nodes employing the same value are supposed to be very low. Okay? That's one thing. Second, every node, when they configure an address, they do something that is called duplicate address detection. Well, obviously, the name implies that whenever you configure an address, you check whether somebody else is using that address. And if somebody else is using that address, then you select a different one. Okay? The traditional way of selecting the interface ID was to embed the MAC address in the interface ID. You do a few modifications, but at the end of the day, it's like embedding the MAC address in the interface ID. Can anybody think, I mean, we're going to discuss that afterwards, but can anybody think of what could be the benefits or why would you put the MAC address in here, and what are the drawbacks? Like, what's the good part and what's the bad part of putting the MAC address in here? Exactly. So the point that he made, he said, well, they are usually different, which in theory is true. Like, in general, MAC addresses are supposed to be globally unique. So you shouldn't be able to find two different nodes with the same MAC address. Now, there are companies that reuse the MAC addresses. They shouldn't, but they do. Like, there are guys that did studies, like, scanning systems or measuring the MAC addresses, and they found that, vendors, I don't know if they ship the devices to different places. Like, okay, they reuse MAC addresses here, in Brazil, and in some other place that is far away, and they assume that you are not going to use those devices in the same place. But in theory, they are unique. Uh, and that's a good thing, because if you can select from the MAC address a number that is unique, well, you even reduce the chances of collisions even more. You are coming with a number that is, by default, is unique. So the chances of two systems selecting the same address are very, very low. Now, what's the drawback of this? I mean, that's the good part. What about the bad part? The what? Yeah. Well, what he said was you can change the vendor by looking at the IPv6 address. That's what you said, right? And more generally speaking, if you include a MAC address in here, you are doing an information leakage. I mean, the vendor is true what you say, but it's actually even worse than that. Let's say that we come to this conference and somehow I know your MAC address. Somehow. You send me a packet, I sniff the network, whatever that is. Now, if wherever you go, you put your MAC address here, I can simply identify your identity by looking at the interface ID. Because you are putting a number that is globally unique, you are the only one that is supposed to be using that number, and you put that number in all the packets that you send. That's awful. Like, from a privacy point of view, that's awful. You don't even need to get to the application layer to figure out what's the node that is sending you packets, because the node is putting a serial number in the IPv6 address. That's horrible. But, you know, at the time that this was developed, was like in the early 90s, this wasn't a concern at that time. You know, in the recent years, let's say 10 years, even more in the last few years, it became much more of a concern. So the IETF is moving away from this. But in most of the cases, and I can show you a simple example, so look at this. This is my network interface. This is my MAC address, okay? Now look at, for example, this one. Does it look familiar? There are a few things. I mean, for example, if you look at this and this, it's the same thing, right? Now, obviously, I read about it beforehand. It's not that I'm smart. Since the interface ID has to be 64 bits, but the MAC addresses are 48 bits, well, you have to put some crap in the middle to make it a 64 bits number. This is the FFFE. You always put the same value in there. That's so that you fill up the space that otherwise you could put it in blank, okay? And there's another thing, that there's one bit in here that you flip. That's why these 4 becomes a 6. Why? Because, well, it's the local or universal bit in the MAC address. I'm not going to get deeper into that, but, you know, just to make things short, when you look at the interface ID, it's the same thing as the MAC address, except that you added these 2 bytes, which you always add, and you know that you flip 1 bit in the most significant byte, okay? But obviously, if you know the process, from this, you can obtain the MAC address. You just remove these 2 letters, and you flip back the bit that you originally flipped, okay? Again, from a privacy point of view, that's horrible. What other things you can do? For example, you can write the address in this way. This is the same way that I showed before, which kind of like embeds an IPv4 address. Why do you think you might want to do this? Well, it's simple. This is for practical purposes. Let's say that you are let's say you administer the network of an ISP and you remember the IP addresses of the routers or the servers. Now, if you have to put an ugly number like the MAC address, but either you don't remember or if you have mental problems, right? If you are remembering all those numbers. Now, if you embed the IPv4 address, then as long as you remember the IPv4 address, then the IPv6 is easy because it's just the prefix and the IPv4 address. Then there are low byte addresses. This is what you might expect. If you are configuring, let's say, a web server or a mail server or something on your network, well, normal people usually put all zeros and some small number there. You don't want, I mean, eventually you might need to, connect to that system just by using the address, and you don't want to have to remember BDF456, okay? it's quite easier to just put an address that is just the prefix, all zeros, and just the number of the server. Okay? Then there's people that do this kind of thing. I mean, since these numbers are hexadecimal, you can write some words in here. I don't know if it still works, but do you see that? That's IPv6 address for Facebook. Obviously, this wasn't coincidence, right? You might wonder about these people. These are people that you probably want to keep them away if their concept of fun is to do this kind of thing. But at times you find this type of addresses, like with words that have been encoded in the IPv6 address. And there are some transition technologies that we're not going to discuss, but there are some, let's say, tunneling protocols that require you to select the interface ID in specific ways. What about link local addresses? The interface ID part is exactly the same thing. It's just an interface ID. The same considerations as before apply. Obviously, the only thing that changes is the prefix. So you use FE80/64. For unique local unicast addresses, the structure is the same as the global addresses. The only difference is that you use a prefix. This is the equivalent to the, let's say, the 192 blah 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 from IPv4 world. Now, let's look a little bit more into detail about how the interface IDs are selected. This is what I said about embedding the MAC address, okay? Low order, 24 bits of the MAC address go here, then this fixed word, then the rest of the MAC address. And you have to flip this bit, universal local bit, of the MAC address. Okay. Second one, there are addresses that are called temporary addresses. At times they are they are identified by the specification that, specifies the algorithm. What are the addresses about? Essentially, you select them. They have two important parameters. First of all, the interface ID is a random number. Second is short-lived. So they only last for a small period of time. Okay? That's supposed to be good for privacy. Why? Because if you have an address that is a random number and that is changing all the time, well, obviously, by looking at the interface ID, now you are not disclosing the vendor, now you are not disclosing the identity of the node, etc. These temporary addresses are usually generated along with the traditional addresses. So the idea is that in those cases in which you use temporary addresses, you have stable addresses and you have temporary addresses. Typically, you use the temporary addresses for outgoing connections, like when you act like a client, okay? Now, if you want to receive incoming connections, you use the stable address, for obvious reasons, right? If a server was using temporary addresses, you would have to be updating the DNS all the time. Interface IDs in Windows. Essentially, Windows does a different thing, something that is not compliant with the standards. The stable addresses in Windows, they are just a random number, but that doesn't change over time, okay? The reason for doing this is so that, for example, you don't leak the vendor in the interface ID. Now, I was telling you that, that of embedding the MAC addresses in the interface ID has problems, okay? One of the problems is, revealing your identity. You are putting a number that is globally unique. Everywhere you go, you put your MAC address in there, okay? Now, trying to get ahead a little bit, how do you think that embedding a MAC address affects network scanning? I mean, we're going to discuss that, but I'm just, moving ahead a little bit. Is there a microphone for them? No.
We invite you to
Okay, so if I understood correctly what he said, and if not, I'm correcting it. So what he said is that if I'm scanning a network and I know that they generate the addresses by embedding the MAC address, I don't need to try like random addresses. For example, let's say that you know that there is a company that buys all of the devices from Hewlett Packard. There's no reason, if you go here, tip, 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 this is the identifier for the vendor. So if you know that that company only buys devices, from Hewlett Packard, obviously when you're trying addresses, you will always try the one that here they have the number that identifies Hewlett Packard. Not Dell, not something else. So to put that in a different way, this helps the attacker reduce the search space. Originally we said, well, the network, so the addresses are 128-bit long, okay? Each subnetwork is 64 bits, the interface ID. Now, really, if you think about it, well, actually, these 2 bytes are fixed. So from those 64 bits, there are 2 bytes that you always already know what they are, FF, FE. Now, the 3 bytes that you have over here, if you know the vendor, one way or another, then you can reduce the set of values here. Maybe you don't know the exact value because there are vendors that have multiple values for the IEEE OUI, okay? But at least you can reduce the values in like, let's say, 10 values, 20 values, 50, okay? Uh, yeah, I mean, but what you mean is that you use using a different scheme, you mean? Ah, yeah. Yeah. So what he's saying is that, well, if you have a network, somehow you could hide some systems if all the devices, follow this logic, but then the ones that are supposed to be important, you just set them manually. It's true, you can actually use it, you can do that, but at the end of the day, you could hide all of them. Yeah, I mean, there's some part of true in what you say. I mean, thing is that if you really have to scan like the whole 64 bits, something's going to break before you actually find the nodes. Other ones, temporary, we cover, Windows, we cover. Now, I was telling you about the problems with embedding the link layer address, embedding the MAC address. So RFC 7217 is a standard that I published to replace the traditional scheme, okay? To do something different. So if you look at, let's say, IPv6 implementations, let's say older than 2 years, all of them put the MAC address in there. If you look at IPv6 implementations right now, some of them, they already do this. So the scheme is quite simple. Just for a second, I mean, and we can make things even simpler than this. For a second, just assume that you compute a hash over a prefix, forget about all this, and a secret key. So forget about all of these parameters. Obviously, they are useful, but not this, just the prefix and a secret key. Secret key, obviously, is supposed to be secret and unique, okay? Let's assume this. Let's say that you generate the interface ID with this expression. You connect to the network. You have some prefix on the local network. The secret key is unique and it's secret. So essentially, the result of this is going to be like a random number, okay? Sorry? No, but the thing is that when you have a hash function that is supposed to be cryptographically secure, well, this has to be, let's say, the strength of the function relies on, the key being secret. So the idea is that, let's say that I know that you generate your interface ID with this function. The hash function that you employ, I might be able to know which one. Let's say it's SHA, for example. The prefix, I know because it's advertised on the local network. But I don't know what's your secret key. So I don't know in advance what's the number that you're going to generate. Now, you connect to a network, there's a prefix that is employed on the local network, you have a secret key, you get a random number. Now, what happens when you move from one network to another? Sorry? Well, it will work, but the thing is that when you connect to a different network, the prefix will change. And if something in between here changes, the result is going to change. So what does this mean? That when you move from one network to another, you are kind of like guaranteed that your interface ID is going to be different. That's like a feature of this algorithm. That you put the prefix in as one of the parameters of the hash function, so that when you move from one place to another, you are sure that your address, your interface ID is going to change. Huh? Well, no. The secret key is just for your host. It's local. For example, the secret key could be a random number that you compute when you install the system. Okay? Now, a feature, or the reason for which we did this, as opposed to just a random number, is that from an operational point of view, you want the addresses to be stable within the same network. Why? Let's say that you are administering like a university network, and there was some system that got infected. If the addresses are changing all the time, well, I know that system 1, 2, 3, AB, blah, 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 got infected. Well, I don't even know what that is, because the addresses are changing all the time. So from an operational point of view, there's value in the addresses remaining the same while the systems are connected to the same network. Now, if you think about this, you connect to one network. The prefix is some number, you have the secret key, you get an interface ID. You move to a different network. The prefix changes, you get a different interface ID. Now you move back to the same original network. Now the prefix is the same as before. And that means that you're going to get the same address. So when you go back to the same network, you always get the same address, even without having to remember in your system what's the address that you got before. Okay? That's a feature of this. I mean, obviously, there are more parameters that you need to include here, and I'm going to describe just one. You have to put something that is an identifier of the network interface. Why? Because if I have two network cards that connect to the same network, if I only use the prefix and the secret key, both interface cards are going to get the same address. So there has to be something that helps differentiate between the cards. And this is the network interface, okay? But these are just details. So the properties of this is that you get addresses that are unpredictable, because if you have many nodes in the same network, there's no pattern, like every node gets like a different random number. The addresses are stable within the same network, but when the node moves to one network to another, the interface ID varies. When you come back to the same network, you get the same stable address. So it's like a trade-off. You know, on one hand, getting, random addresses. On the other hand, getting something that from an operational point of view, it's nice. I mean, obviously, from a security point of view, you could say, well, I want random addresses that change every minute. Well, yeah, but then the poor guy that is administering the network is going to have a nightmare. You know? It's always a trade-off. You might wonder about implementations. First implementation of this was in the Linux kernel, 4.0. Then this was incorporated by Network Manager too. Network Manager, essentially, when you use, let's say Ubuntu or Fedora or whatever, the actual network configuration is done by Network Manager, okay? And there's another, application package that is called DHCP-CD, which is employed, for example, I think NetBSD employs that, but also in Raspberry. If you use Raspbian, let's say the software that they use for network configuration is this. I learned about this because I was editing the usual files, and I didn't get the changes that I expected. So I said, who's configuring the addresses? Well, eventually I learned that it was this application. Now, what does that mean in practice? If you download a current version of Fedora, they implement this. So you will see that for example, the addresses are not, they don't include the FFFE anymore, and they don't include the MAC address anymore. Okay? That's obviously an improvement. I don't know if I have a Fedora box here. Say. No. Okay. Well, this one I mentioned, if you put IPv4 addresses in the interface ID, it's easier to remember. Oops, that was fast. Okay, beep beep. Now this is one that is interesting. I mean, as a side comment, I like to do like a bit of, more theoretical stuff, like, writing specifications, but I also like to run tools and send packets. Why? Well, because usually when you do stuff, you learn stuff that you can, include in papers, and the same way around. In a paper or in something that is more theoretical, you can come up with ideas that you can, move into code. Now, when I was scanning V6 networks, and it wasn't just me, there were a few other peoples, we found out addresses with these patterns. For example, there's people that when they set the addresses of web servers, they set the number 80 as the less significant byte of the interface ID, and then they use another number to identify the web server number. So let's say if they have two web servers, the first one is 180, the second one is 280, and so on. Other people do it in a different way. They put the 80 here and then the number here. And then there's people that for me are mentally insane. Whoops. That rather than putting the value 80, they translate that into hexadecimal. For me, that's like brain damage at its, perfection. I don't know what they do. It's like they are way smarter than me, or that they have problems. But they do this. So we found like a lot of with the number 50 here, and then we say, well, what's 50? Because there's no popular number. Now, it turns out that there's 50, and 50 translates into 80, and they do the same for like, SMTP. If I understood his question correctly, he was saying, what do you do, or how you can represent an address followed by a port? Like that's what you asked. Like in before, you can write like IPv, like an IP address and then colon and then the port. In IPv6, you have to include the address between brackets. The brackets essentially say where the address ends, and what follows is the port. What else? And these are the easier ones. Like, if you are configuring servers, normal people, they just use all zeros and they just vary the last byte. So first server is :1, second one, :2, and so on. Some people, for reasons that I don't know, they use two small values. This could be like, I don't know, but they use two small values, okay? So those are the unicast addresses. This is multicast. So in IPv6, we don't have broadcast anymore. In IPv4, you could send, at the time, for example, remember the SMARF attack, you could send a packet to a broadcast address of a remote network. Then you'd have all of the systems in that remote network responding to that packet. Well, that has been removed from IPv6. But there are multicast addresses that can be employed on the local network. Just to give you an example, this address in here means all nodes on the local link. Okay? So if I send something to this address, I'm sending my packet to all of the systems connected to the local network. We can give that a try. Oh. Oops. Ping menos... qué boludo. So what did I do here? I sent a ping packet to a multicast address that represents all nodes on the local link. Okay? This is like sending a packet broadcasted on the local network. Okay? You might wonder, if you look here, why did I have to specify the interface? Why? Because? Well, exactly. Or another way to put it is that this address is, if I have a system with two different interfaces, well, I had to tell my computer on which of the two interfaces I want to send the packet, okay? So this is an example, and this actually teaches you a different lesson, or you can learn something else from this. This network is not supposed to support IPv6. Still, when we send a packet to a multicast address, we get a response from 10 systems. So whether the network supports IPv6 or not is like, well, in practice, you always support IPv6 to some degree. So you might say that you don't have global connectivity because all of these addresses are linked local. So yeah, these nodes cannot connect to the global internet, but as long as I'm on the same link, I can send packets and connect to these systems if they have an open port, for example, okay? Okay. Oh. Well, there are other addresses, like, for example, this is for all nodes. This is for all routers. So if rather than pinging this one, you ping this other one, you are going to get responses just from the routers. Let's see. Well, I get at least one, okay? Because it has to be, most likely because it has IP forwarding enabled. So by definition, a router is some device that is able to forward packets from one place to another. So these are commands that you can use in different operating systems to check what are the multicast groups or multicast addresses that they are employing. Let's say if you run this command on Linux, it will tell you what are the multicast addresses that Linux is listening to. Obviously, as you can possibly expect, at least it's going to be listening to the all nodes multicast address. That's why it responds, okay? Okay. So, in all this part, what we did was we discussed, let's see where we are, okay. We discussed the structure of IPv6 addresses, okay? The different scope, the different ways to select the interface ID, and so on. Obviously, if you spend a lot of time playing with IPv6, there's going to be a point in which you look at an address and you can easily tell what's in the interface ID, what's the scope of an address, etc. When you look, for example, at an IPv4 address that is 127, blah, 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 you know it's loopback. Why do you know it's loopback? Because you have seen that address 100 times. That's the reason. You look at an address that is 192, blah, blah, blah. It's a private address. Why? Because you have seen that address 100 times. Well, with IPv6, it's the same thing. First few times, well, you look at the addresses, they are going to look like garbage. Eventually, you will get used to them. Now, at some point in time, I mean, the real purpose was something different, but I realized that I needed to build like a tool to be able to process addresses, like to make the life easier for a person that is, dealing with addresses. So I did this tool that's called address6, the same one that we used before for printing the canonical addresses. Now with this option, -A, what the tool does is analyzing the IP address that you give as a parameter. And let me give an example. Let's say so the address that I came up with, is this one, okay? Obviously, I selected this one on purpose. So that is a global address. The prefix is a global prefix. Now, if you look at the interface ID, you can see that all the bytes are set to 0. That's why it has all the compressed, the colon. It's full of zeros. Now, we were saying before that when the interface ID is all zeros and you just have a small number, we call that low byte address. You know that the address contains the prefix set to all zeros, and it's just the last byte that varies. So what the tool is still saying over there is, it's a unicast address, in the second line here. It's a global address, second subtype, global, and the interface ID is, the category is low byte, and the subcategory is unspecified. It's like, that's the category. Let's do the same experiment, but let's say, with this one. What would you expect now? The address is global unicast, again, but what the address says is that the interface ID is derived from a link layer address. That's why it says IEEE derived. And here, that's the IEEE OUI. That's the number that identifies the vendor. If you look at this bit has been flipped. So now you take this number, you go to the IEEE OUI database, you search for this, and you can tell what's the vendor of the network interface card, okay? I mean, as you can probably expect, the output is not very human-friendly because I was expecting this tool to be used by a script, okay? So actually, I ended up using a script to process this data. Well, these are just examples. Like, you can run the same thing. Let's say, oops. I'm going to just do only one more. As you can expect, this is a link local address. Why? Because of the prefix is FE80. The interface ID, again, is low byte, okay? Now let's change something. Let's assume that I do this. What do you expect the interface ID to be? Randomized. Well, it's just crap that I put here. Random numbers, okay? I mean, obviously the tool has to do some heuristics. I mean, and there are cases in which the tool is not sure, but it tries to, be able to analyze if the address follows patterns. Let me give you, I hope this one works. It might not work. Look at this address, okay? I mean, it's not a MAC address, but it's also not a low byte address. But it does follow some kind of pattern, right? Because there are, like, for example, there's 1 byte in every 16 bits that is set to all zeros. Wait, no. There's a reason for that. I will explain later, but let's do this. It says pattern bytes. What does it mean? Well, when the tool looks at this address, I mean, there's some kind of pattern in there. I cannot tell what's the pattern, but clearly there's, 1 byte in every, 16 bits that is set to 0. So if, for example, you learn one address of a network, and the address is like this, and you wanted to scan that address, what would you do? Well, obviously, you would set in all of the other target address, this to 0, this to 0, this to 0, and this to 0, and you just vary these ones. Because that's the ones that apparently are, changing. The other stuff is supposed to be 0. Okay. Other things. These ones I'm not going to, run them on the command line, or, well, I could run one, I guess. Let's say. Let's say, so this is just a text file. It has a bunch of addresses, okay? And all of them seem to be global except for the last one, which is link local, okay? If I'm doing some kind of, obviously this is like a short file. This you could sort just editing the file. But if this file had like 1 million addresses, I mean, doing this by hand would be like not nice. You can, let's see. You can use this address 6 tool to filter addresses that you have in a file. Let's say you have a bunch of addresses in a text file, and you want to tell the tool, well, I only want to keep the addresses that are global. I only want to keep the addresses that are link local. Or I only want to keep some specific kind of address, like addresses that belong to a specific prefix. So let's look, for example, at, if I understand this correctly, let's see. Whoops. Did you see what I do? Wow. So first, this is the file, okay? It has all the addresses. Now, I pipe the contents of the file to the address 6 tool, and I tell the tool I only want to accept, let's say, keep the addresses that are link local. So the only one of all the addresses in the file that the tool gives me is the link local. I could do it the other way around. Now, when I ask for the global addresses, I get all of them except the one with FE80, okay? You can specify filters of any kind that you want, like different prefixes, different scopes, different types of interface IDs, and whatever. And again, what's useful for this is that if you try to do something with a remote network, it doesn't make any sense at all that you use a link local address. Actually, if you use a link local address, you think that you're sending something to a remote network, but you're sending that to your own network, okay? So it's always important that you filter addresses in this way.
Поэтому мы продолжаем приглашать вас посещать активно стенды наших друзей и партнеров.
So these are just different types of filters. Another thing that you can do is produce statistics based on a number of addresses. Okay? Let me see.
Безопасности. На стенде представлена практическая реализация решений по автоматизации процесса реагирования на инциденты.
Oh, let's do this.
Станции нового поколения средств защиты рабочих станций и серверов с функциями выявления потенциально опасной
So what I did right now, I did something like this. The same set of addresses, I send them to the address 6 tool, but now I ask the tool to produce statistics. Now, when I look at the output, it says, of the addresses that I have, there was a total of 9 addresses. 9 were unicast, okay? Then of the unicast addresses, it analyzes, for example, the scope and special types over there, and here, where is it? Toop, 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 toop. The tool analyzes the type of interface ID. So what the tool did is that for every single address in the file, it tried to figure out what is the interface ID, what's the technique or the algorithm that it employs for the interface ID, and it gives you the stats. In this case, 22% of the addresses were low byte. Now, what do you think this might be useful for? Why do you think you might want to produce statistics?
Лаборатория Касперского приглашает принять участие в игре «Грабби» активным игрокам в основном компании. За подробной информацией обращайтесь на станцию лаборатории. Он расположен в фойе
To scan those.
этажа.
Exactly. So let's assume this. Let's say that you wanted to attack a specific network, okay? And somehow you have a file with a bunch of addresses of that network. You don't have the addresses of all the systems that you want, but you have the addresses of a large number of them. If you produce statistics like this, and you get something like, 90% of low byte addresses, well, you should scan for low byte addresses, okay? Because it would seem that most of the addresses follow some specific type. So identifying the specific pattern is useful for you as an attacker because it gives you an idea of where the rest of the addresses are, okay?
Будет нас ожидать уже завтра.
And here in conference hall, we can see track the success of hackers and defenders who take part in the stand-up contest. You can see sometimes the results of the
Okay. So this is essentially like the theory behind the addressing architecture. So it's not that we discuss this because it's nice, but rather because if we want to understand the scanning part, we have to know the theory behind how IPv6 selects the addresses. So now let's go to the scanning itself. That was the whole reason for discussing the addressing architecture. So I was saying that to the extent that it's possible, I try to compare everything in v6 with IPv4. In v4, when you do an address scan, usually you do it by brute force. Why? Networks are so small that it doesn't make sense to use your brain. Just scan every address, and you can get away with that. You can do that with IPv4, but not with IPv6. Why? Because each subnetwork has 2 elevated to the 64 power. So there are so many possible addresses in there that if you just want to scan from address number 0 to all Fs, well, that will take forever, okay? So it's not possible to do a scanning attack by brute force. Now, when we think about scanning networks in IPv6, actually we have to differentiate between 2 cases. One case is scanning a local network. The other case, which is completely different, is scanning a remote network, okay? One is way simpler than the other one. Local network, rather easy. Remote network, more challenging. What would you do, for example, based on what we have discussed so far, what would you use to scan a local network? Exactly. So if you want to scan a local network, there's no point in trying every single address because you have the multicast address which identifies all the nodes in the local network, okay? So just, you might say, okay, just send a ping packet to that address and that's it. All the systems will respond. And in theory, that's what you do. Now there's a caveat, there's like a small detail in there. Microsoft Windows doesn't respond to ping packets sent to multicast addresses. So if you send a ping packet to a multicast address, you get response from Linux, from BSDs, from macOS, but not from Windows, okay? Which is useful in a sense, but obviously you want to find all the systems, okay? Now, I started, coding the tool, essentially doing the tool what internally does is send a ping packet to a multicast address. And I say, well, I got all of these nodes, but I still need to find the Windows systems. Now the question was, what's the crappy packet that I can send to Windows that they will respond? Yeah. But what kind of packet? Yeah, well, I mean, the thing is that if you, so what he says is that you could send a neighbor discovery packet. That's the equivalent to ARP. But that will only work, I mean, with ARP, you get responses if I ask for your address. So it doesn't make sense. That's the equivalent of trying every single address. Now, when I was reading the IPv6 specification, there's one part of the spec that says, if you send an IPv6 packet with options, meaning you put an extension header, do you remember one of the first few slides? You put an extension header and you put an option that is undefined, all of the nodes must respond with an error, with an ICMP error. And that actually worked. So what you do is you send the ping packet just in case, but then you also send a packet with an unknown option and Windows responds to those. So if you want to do like, I mean, obviously, it doesn't make any sense to not respond to ping if you're going to respond to something else, but so the scanning tool that I produce essentially sends two different types of proofs. It sends normal multicast echo requests, the same ping packets that you could send with the pin6 tool, but also sends an undefined option. The particular naming here doesn't matter. It's just an option that hasn't been specified, okay? Or, if you want the reasons for this, the standard says that if it's an option that is unspecified, it hasn't been standardized, and it starts with this, you have to respond with an error. If the option is not specified, but for example starts with something different, you can ignore without responding. Obviously, you want an option that the nodes will respond to. That's why you use the ones that start with this, okay? So the scanning tool, obviously, it sends two different types of proofs. Multicasted ping packets, and it sends ping packets with an option that nobody supports. This way, you get the Windows systems to respond to, okay? Now, there's another thing. Let's say that, I was saying before that whenever you have an IPv6 node, that node typically configures many different addresses for the same interface, okay? Many different addresses for the same interface. Like in the same interface, I can have addresses with different prefixes, I can have a link local address, and so on. And I wanted the tool to learn all of the options, all of the addresses, okay? Think about this. If I send a packet, if I just send a single ping packet, well, I will learn just one address of that node. Maybe the link local address, maybe the global address, but not all of them, okay? Now, if you want to learn all of the possible addresses, what you have to do is send the ping packets or the proof packets with different source addresses. Why? If you send, for example, a multicasted ping packet from a link local address, all of the nodes will respond with a link local address, okay? So I send the multicasted ping packet using a link local address. This way, I learn the link local addresses of all the nodes. Now, let's say that I know that in my network, there's some prefix that is being employed. if I send the ping packet with that prefix, then I will learn all of the addresses from that prefix that the local systems are using, okay? So by using different source addresses from different prefixes, you learn all of the addresses of the local nodes. Now, if you take this into practice, I mean, obviously it's all transparent. If you run the scanning tool like this, -I, it specifies the interface, and -L, that stands for local scans. The tool, essentially sends the two different kinds of proofs on the local network. So as you can see, first of all, the tool learned the link local addresses. Then it also learned the global addresses. But when we were trying to ping, the local network, when we did the ping before, we only got link local addresses. We didn't get the globals. You understand what I mean? So before, when I did this, ping 6, this means all of the nodes in the local network, I only get link locals. Obviously, from the point of view of an attacker, in general, what are the addresses that you would prefer? The link locals or the globals? The globals. Because if I learn the globals and they are not filtered at the border of the network, I can employ them from everywhere. Now, the link locals I can only exploit if I'm connected to the local network, okay? Let's see, -E. If you want, I mean, that's just a small detail. You can request the tool to also print the MAC address. And why you might find this useful? Well, because, for example, if you look, let's see, For example, this node and this node obviously are the same. Is true? Yeah. Why? Because the MAC address is the same. So the point of, printing the MAC address is because, well, with just one other script, you can say, well, I group all of the addresses for a specific node. If you just look at the address, well, it's not possible to tell that. But if you look at the MAC address too, then it's possible to tell, which addresses correspond to the same system. So this is for local scans. Local scans, again, are way simpler than the remote scans. Why? Because we have multicast addresses. So rather than having to try every address, I use a single address that identifies all systems, okay? Then we have the small problem of Windows not responding to multicast pings. But then you send a packet with an option, and then you get responses from Windows. So the problem is solved. Now we're moving to a different problem, which is scanning remote networks. Now, when you scan a remote network, things are more complicated. Why? Because you cannot use multicast. So it's not that you can send a proof packet to a single address and you get responses from everywhere. Now you have to do something else. So in the first time that I presented on this topic, I already knew that there was people claiming that address scans attacks in IPv6 were impossible. Now, in IPv6 in general, you hear a lot of claims like crap, you'd say, and there's two options. Like, option one is like you say, well, these people smoke something, so they are just talking nonsense. And then you have another option, like maybe they have some kind of reasoning for which they claim what they claim. This is a quote that I actually got from the internet. It's not that I came up with this. It's like, most likely if you search for this verbatim, you will find that some guy actually said this. So I was trying to be a nice guy, and I said, well, let's assume that the guy that said this wasn't under the effects of any kind of narcotics. So he actually had a reason for claiming this. So I assumed that his logic, or her logic, was that he was assuming that whenever you wanted to scan an IPv6 network, the search space was 64 bits. Okay? if that's your reasoning, if you assume that whenever you want to scan an IPv6 network, you have to try all of the possible addresses in 64 bits, well, that's impossible. Or it takes so many years that by the time you finish your scan, probably there will not be any human beings on the planet. So now, let's think a little bit more about scanning based on the stuff that we already discussed when we were talking about the addressing architecture. Let's assume that the interface IDs of the addresses are randomly selected, random numbers. If they are random numbers, we are screwed because in all the search space, you have the host in any part of the search space. There's no pattern at all because the addresses are selected randomly. And in that case, you have no other option than do a brute force, like scanning the whole space. Now, when we looked at how addresses are generated, we saw that most of the techniques to select the addresses actually follow patterns. It was only that RSC that I told you, the one with the hash that was published recently, that tries to select the addresses randomly. So, if the interface IDs are random, we are in trouble. Scanning a B6 network is going to be like quite hard. Now, if the addresses follow some kind of pattern, then the search space is hopefully going to be like, smaller, and then probably it's going to be feasible. Then we will have to see whether that's a matter of seconds, minutes, days, weeks, or a year, but at least feasible. Okay. Another thing that, complicates the analysis is a little bit is that different networks and different implementations employ different algorithms. So actually, to be able to respond this question of, whether in practice, the addresses follow patterns or not, what we had to do was to look at real networks and look at real addresses, how they are selected. When I was studying this, well, this looks awful. I don't know why. Let's see. Bueno. Jeez. No. Ow. Well, this is better. Ah. Well, I don't know why I cannot change this one, but when I was studying this, I tried to find out if anybody had tried to analyze how IPv6 addresses are selected in practice, okay? So there was this guy, David Malone from Ireland, a university in Ireland, that what this guy did was he did two different experiments. The experiment one, he was running, I don't know if it was a web server or an FTP server, and he had a log file, like recording every address of the systems connecting to the FTP server, okay? So he recorded the addresses for I don't know how long the period of time, and then after that, he used some kind of tool, not mine, but some tool made by his own, and tried to analyze what patterns, if any patterns, were being followed by those addresses. So this is what he found for clients, like clients connecting to his web server or clients connecting to his FTP server. 50% of the addresses were Slack. Slack are the addresses that incorporate the MAC address, okay? So all of the systems that connected to his server, 50% were using a MAC address in the interface ID. 20% were using an IPv4 base address. So that means that in the interface ID, you put an IPv4 address. This is a technology created by Microsoft that, thank God, nobody uses anymore, so forget it. Then there was an 8% of low byte addresses. Low byte are addresses that contain the interface ID set to all zeros and just the last byte that varies. Now, regardless of each category, if you look at this slide, it should be clear and quite evident that the addresses are not random. They do follow very clear patterns, okay? 50% of the addresses, for example, incorporated a MAC address. He did the same study for routers. For the routers, I think that what he did was he ran traceroute with random systems, and then he captured the addresses that he obtained from traceroute. Now, if you look at the stats, they are quite different. 70% of the addresses are low byte. And that makes sense, because usually for routers, you configure the addresses manually. And, and if you are kind of like, okay, from here, that's the way in which you do it. Like, all zeros, and then you put a small value. Then 5% were addresses that incorporated an IPv4 address in the interface ID. And I was saying before that one reason for doing that is because it's easy to remember the B4 and the B6 address of the node. So if I remember that the IPv4 address of a router is some specific address, well, it's easy to remember the B6 part because it's just the IPv6 prefix and the IPv4 address. Now, when I was looking into this, I said, well, these measurements are okay, but they are dated. They were old. I mean, he had measured this like, 5 years or 6 years ago at the point I was studying this, and I knew that many things had changed. Like what? For example, at that point in time, many systems were already using temporary addresses. And here, you only see like a 6% of temporary addresses. So I said, well, this is because he measured this like 6, 7 years ago. If he makes this study again, the numbers are going to be quite different. So I sent this guy an email. I said, could you please like redo your experiment? And he didn't have the time. So I said, well, I need the numbers. So that's why I started to create tools about that. The address 6 tool that I was using before, actually I created that to be able to do this. To measure the addresses and incorporate or try to figure the categories for the addresses. So, even when the numbers are dated, one thing that is clear from the numbers of this guy, David Malone, is that addresses do follow patterns. They are not random. Now, his work motivated a different study that I did myself. And this is what I did. Obviously, I needed a bunch of IPv6 addresses. And I don't run any popular web server or FTP server or nothing like that. So I said, well, I need to get addresses from somewhere. So what I did is I grabbed the Alexas. You might know that. This company, Alexas, I don't know what they do, but they provide a nice file with the top 1 million most popular sites. So here you have essentially 1 million domain names. So what I did was, for each domain name, I tried to obtain the quad A records, like the corresponding IPv6 addresses. And then there was another site, World IPv6 Launch Day, which contained the domain names of popular websites that had enabled IPv6 on this day, the IPv6 Launch Day. So this was just another source of data. So by obtaining the quad A records for this and for this, now I have a bunch of addresses corresponding to web servers, okay? But I said, well, but actually I like addresses for other stuff, like, not just web servers, different kinds of servers. So using the same domain names, I obtained the NS records. NS records has the records for the name servers, and then the quad A records for the NS records. So this means that for a given domain name, now I have the IPv6 addresses for that domain name. Okay? Now I have B6 addresses of websites, B6 addresses of name servers, of DNS servers. Another thing that I did was, for all of these domain names, I obtained the MX records. MX stands for mail server. And then from the MX, I obtained the quad A. This means that now I have addresses for web servers, name servers, and mail servers. Okay? Different kinds of servers. Maybe the results were going to be the same, maybe not. Okay? So these are the results that I got. The results on this side corresponds to the data set of the World IPv6 launch day. The results on this side for Alexa's top 1 million sites. The reason for which there are two cakes is that in the first one, it contains the stats of all the addresses. In the second one, duplicate addresses have been discarded. And you might say, well, why do you want to count an address twice? Well, it's a different kind of measurement. If you count the addresses once for each time that it appears, it's like a weighted statistic. So an address that is used for many sites is more important, counts more. Now, if you just don't use duplicate addresses, you are measuring a different kind of thing. Now, here you have the stats for, different patterns. Clearly, when you look at web servers, almost half of the addresses are low byte. Okay? And then there is a large percentage, which is addresses that embed an IPv4 address. Now, if you summarize or if you add the part in light blue and the part in red, you almost have already 70% of the addresses. Yeah, obviously, you still don't have these ones, I don't have these ones, but you have a large part of those. So, if you were, let's say that you were trying to scan some of, let's say you were meaning to scan the internet for web servers, would you just try random addresses? No, obviously not. You try, first of all, the low byte addresses. Second, you try the addresses that embed an IPv4 addresses. That helps you reduce the search space. Once you have found this and this, then you can try something more funny to try to find these nodes. But obviously, the first systems that you want to find are the ones that are easier to find. Now, this is for web servers. Now, I still have data for name servers and for mail servers. This is for mail servers. An extremely large percentage of the addresses are low byte, even more than before, okay? Now, if you want to scan a network for mail servers, do you try random addresses? No, obviously not, because most of the servers you employ low byte addresses. So yeah, in theory, the interface ID can have 64 bits. Now, in practice, since most of the networks just use like the last byte for selecting the address, you don't need to try by brute force the 64 bits. This is for DNS. So DNS is kind of like quite similar to mail servers, but it's kind of like different from web servers, okay? Now, there was these last three slides that I presented. They essentially represent how addresses are generated for internet servers. Now, you might wonder how the addresses are generated for clients, like a normal host that communicates to the internet. When I published the previous 3 slides, there was a guy that I knew from a conference that he said, well, I run a popular web server. I have like a log full of IPv6 addresses. If you send me the tools, I can run the tools, for the addresses that I have. So he ran the tools, and these are the numbers that he got. A quite large percentage of the addresses are random. Now, there's a trick here. There's a trick here. This might be misleading if you don't keep in mind some of the things that we discussed before. These random addresses are temporary addresses. And I was telling you that temporary addresses are configured in addition to the traditional addresses. So you have the temporary addresses that are random, and then you have the traditional addresses that include the link layer address. This guy was collecting the addresses at a web server. And I was telling you that for outgoing connections, clients use the temporary addresses. Now, these same clients that employ the temporary address here, they still have the addresses that follow patterns. We are just not seeing them here because when they connected to the web server, they employ a random address. But still, they still have configured addresses that are predictable. So what you can, let's say, read or conclude from this slide is that somehow you measure the number of, the extent to which, I think that's, well, it's my, thanks. It's alive? Yeah. So fine, there's these, if you find it, if not, doesn't matter. Okay, cool. Well, somewhere. Okay, so let's say the moral of the story with this stuff is that we know that a bunch of clients are using temporary addresses, but this doesn't mean that they are not using predictable addresses along with the temporary addresses. Okay, so these systems could still be scanned. This just means that when they do connections to external systems, they use randomized addresses. That's it. Okay. So what are the takeaways from these measurements? Server addresses clearly do follow patterns. So the addresses are not random. If you want to scan for servers, you don't need to do a brute force scan. You just can target the specific patterns. For clients, passive measurements, like the ones of, when you collect addresses in a log file, they don't make much sense. They don't help you from the point of view of an attacker trying to do an address scan. Why? Because the only address that you measure are the temporary ones, the random ones. But you don't know what are the predictable addresses, the addresses with patterns that these systems are using. Now, given that we have discussed the addressing architecture and that we have studied the patterns, now what we're going to do is use tools to exploit these to actually be able to scan networks. First of all, let's start with the addresses that embed a link layer address, okay? So the interface ID is this. This and this is the MAC address, and you know that you put this fixed word in here. What's the search space for that? Well, this part is predictable. It's always the same. If you know the vendor, then this part is the search space for this is not 24 bits. It's going to be like 10 different values, maybe 50 values, maybe 100 values, but certainly not 24 bits, okay? So the only part that is kind of random is this part, okay? But not even so, because when vendors manufacture devices, they don't randomize the addresses, the MAC addresses, so they select the addresses sequentially. So do the experiment, because I did it. You go and buy to some store, and you buy any kind of device. For example, I bought like a couple of IP cameras, okay? Now look at the MAC addresses. Probably only the last byte is the one changing. Why? Because it's like, the manufacturer produces the cameras, and well, they get all these cameras together in a box, and they ship it somewhere. So if you put all the cameras at the same place, chances are that you're going to get consecutive MAC addresses, okay? So I don't know if you play this game here, a game called Naval Battle. So it's like you have like squares, and you are supposed to put bezels on that, but you don't show that to your opponent. And the opponent just has to, try one of those squares, and you tell them if he hits something or not. Well, for this, it's kind of like the same thing. Let's say that there is a company that has 100 systems, okay? And let's assume that they bought all of the systems from the same place at the same time. So you could expect that the MAC addresses are clustered. So rather than trying every single address, in sequence, well, you try this address, and then you try one address like 50, numbers away, so that you're trying to see where the ship in the, naval battle game is. And if you find one address there, then you try the ones that are next to it, okay? And you might wonder about this, like, let's say that I want to target a company, and I know that this company buys their devices from Dell. Well, one thing you could do is you go to the IEEE website, you look for the database, and you manually select, all the IEEE OUIs. Since, I was trying to save time, I incorporated that stuff in the tool itself. So, for example, well, the example I'm going to show after that, but when you run the tool, you will see the example later, you can just specify the vendor, and the tool automatically, it finds the OUIs that correspond to that specific vendor, so that you don't have to do that manually. But it's something that is actually even more interesting. Look at virtualization technologies, like, for example, VirtualBox. If you look at VirtualBox, they have like virtual MAC addresses, okay? So they have to select the MAC address for each of the virtual interface. And for example, VirtualBox always employ the same OUI. So this means that if you have a VirtualBox virtual machine, the OUI is always going to be this. I mean, I can look at, for example, here, any of this. I go to Settings, Network. Do you see here? 080027. I look at a different card. 080027. That happens with, all of the virtual machines, no matter what operating system you have installed. Sorry? No, but you change it, but it randomizes. So what he's saying is that when you install like a virtual box, you change the MAC address. But, I mean, you can manually set any address that you want. If you want, you can do it. But by default, VirtualBox randomizes the MAC address, but always using the same OUI. VMware does something different. For automatic MAC addresses, they use a different OUI, different from the one that VirtualBox employs, but still a constant value. So what does this mean? If I know that I want to target a network that is full of VMware virtual machines and full of VirtualBox virtual machines, then if we look back at this slide, what's the search space here? I mean, this one I know already. This one I know because it's fixed. Now the search space is just 24 bits. And if we were able to scan the whole IPv4 address space, which is 34 bits, obviously scanning 24 bits is quite easy and doable, okay? So how can you employ the tool? One example. First one. You tell the scanning tool, scan6, what's the network prefix, okay? And then you tell the tool that I want to target devices manufactured by Dell. The tool automatically has the IEEE OUI database, so it searches for this, and then it, produces all of the possible combinations so that it only targets, the right prefix and the right interface IDs. I'm not going to run the tool, but I'm going to do something you can, without running the tool, this is dead. Okay. Oh, thank you. Well, scan. Oh. Yeah, 64. Okay. So what I'm doing, I'm running. This is the same example as I had in the, in the slides. And I'm running the tool with a -B option. When you run the tool with a -B option, before actually sending any packets on the network, the tool will print on the screen the address ranges that it's going to scan. So I didn't let the tool run, okay? But you can see that what the tool did was look up the OUIs that are employed by Dell, and only, obviously, they don't change the FFE because that's constant. So what we do is we just scan the low order 24 bits corresponding to each OUI, okay? This means that Dell had 32 OUIs assigned, okay? Now, while the slide didn't say it, let's say you look at the IEEE OUI database, and let's say that you look for Dell. Let's say that the first OUI, let's assume that it was this one, was assigned in, let's say, 1980. Would you expect any of those systems to be used? Not really. I mean, probably they are already away. So what the tool does, before actually printing this, it reorders the OUIs, okay? So first of all, it actually reverses the order. So the oldest one is scanned last, okay? Because that's the one that is older, so quite likely those devices are already phased out. And the other thing is that the last OUI that was assigned, that's like heuristics if you want, is not scanned first either. Why? Because probably the vendor gets the OUI in advance. So the last one that was assigned, probably you don't yet have the devices employing that OUI. So you start scanning, you know, not the last one, but the previous ones, okay? Obviously, depending on the vendor, you have different number of OUIs. Let's say if you look for Cisco, they probably have something like 200 OUIs. Depending on the vendor, you know, whether it's older and newer, and you know the amount of devices that you know they typically manufacture, you get a different amount. Another thing, box. Let's say that I know the prefix of a network, and I know that that network has a lot of VirtualBox virtual machines. So I specify this option, over there, -B VirtualBox, and what the tool does, it just selects the OUI corresponding to VirtualBox, okay? So this is for addresses that include a link layer address. Now, you may remember that I mentioned that some networks, some guys, when they manually configure the addresses of some systems, they embed the IPv4 address in the interface ID. Now, there are two ways in which people do that in practice. This is something that we learn by measuring addresses, not from theory. So one of them was the way in which we discussed already. Embedding the address in this way, so you put the address with the points, okay? With the dots. There's another way of doing that. Some people do it. So you can see here that this address corresponds to an IPv4 address, but it's just like the logic that the guy that manually configured the address used. So there's no like standard specifying this. It's just that if you look at this, you can see that each of the 16-bit words, each of them contain a value that is smaller than 255. So clearly, that looks like an IPv6 address. So you have two different cases. Cases in which the address is embedded this way. So in this case, all this value is in the low order 32 bits. Or cases in which the address is embedded in this way, okay? What's the search space? Obviously, if the interface is generated by means of an IPv4 address, the search space is the same thing as the corresponding IPv4 space. So this is a way in which you can, target these addresses with the scanning tool. Let's look at the. Okay. So in this case, we are telling the tool that we want to target a network that selects its interface IDs by embedding an IPv4 address. But we are considering both options, the two different ways of embedding the address. In the first one, the address is embedded in the low order 32 bits. In the other one, the address is embedded in the low order 64 bits, okay? You can clearly see that the search space is actually very, very, very small. It's just like, 1 byte for, each of the two possible options.
Primeiro, uma técnica qual é fica mais surgir se eles se tranquilam. Mais na próxima,
Now, we were talking about the addresses that embed service ports, okay? And I was saying that, well, there are different options. There's people that put the port number here and the server number here, or the service port here and the port number here, and these crazy people that also translate that into hexadecimal, okay? Now, obviously, it would be nice for the tool to, just come out with the possible ports by itself. So if you run the tool like this, the tool will try all of these 4 combinations, server number and service port and server number, and the same thing in hexadecimal and decimal for, let's say, if I remember, was the 10 top most well-known port numbers, like let's say port 80, port 25, port 21, port 53, and a few others. So let's go back to here, the prefix is the same. So you see that there are many different combinations, but for each of them, the search space is just a number of options. This case, port 21, FTP. And we just try numbers from 0 to 5. Now we change it. We put the service port here and the server number here. Then we do the same thing for SSH. And the same thing for the others. Now this is all in decimal. Then by the end of of this screen, you have the same numbers but in hexadecimal. So that's why they look funny. Okay? But the tool automatically does that for the POP3, HTTP, web proxies, and so on. Oh. Well, low byte addresses are also quite easy. You have 2 options, essentially, or generally speaking, these addresses have small numbers here and here. So essentially, if you want to scan for low byte addresses, just, you have to vary, like scan from 0 to, let's say, 100 here, and let's say from 0 to a few thousand here. So the search space is also small. Same way, you have the way to run the tool is specify the network prefix and specify the address pattern, and then the tool comes up with the address ranges by itself. Now, obviously, being lazy by definition, if you have to specify the let's say the address pattern, that means that you have to be fast enough to look at the address and figure out the pattern, or before doing the scan, running the address 6 tool to actually have the tool identify that by yourself. So last year, I did this. Rather than having, you can still specify a specific pattern if you want, but if not, you can run the tool like this. For example, you put a domain name, /64, and when you specify /64 for a domain name, first of all, the tool will look up the IPv6 addresses for this domain. After that, it tries to analyze what's the pattern in those addresses. And after that, it just targets the specific pattern, okay? So it does the same thing in a few steps. First, it gets the v6 addresses. Then it analyzes the address to figure out the pattern. And then it just targets the specific pattern that the tool thinks that, that network is using. Um, let's see. Poof, 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 poof. Uh, what kind of pattern do you think that they are following? Well, I mean, could be low byte, but there's another one that you might say that they are following. Look at the first few number of ports. 20, 21, that's FTP. 25, that's SMTP. 53, that's DNS. 80, that's HTTP. I mean, obviously, this wasn't, I mean, I didn't try to scan this site just randomly. I know that they use this. I did it before. That's why I decided to use this one. But this is to show you that there are sites that, follow patterns that are kind of like weird, like, very special like this, like setting the IPv6 or the interface ID of the servers according to the service that they are providing, okay? The rest I don't remember, but let's try. Um, ta, 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 ta. No, these don't have this. IETF. In this case, I would say it's quite likely that they embed an IPv4 address in the low order 32 bits. You can see that these two numbers are fixed. Probably, if you translate this to decimal, 68 to decimal, and 14 to decimal, that's the prefix that these same people is using for the IPv4 addresses of the same servers. This should give you an idea that, it's possible to do scans. I mean, if it wasn't possible to do scans, we would be like, the tool would be running without finding anything. What else? Let's try something else. So this looks like low byte, right? Again, what the tool, and you can see here, this is the range that the tool selected as the target. How did the tool decided that? Well, it obtained the query records for this. Now, by analyzing the IPv6 address for this domain, it says, well, it looks like a low byte address. So I'm going just to target low byte addresses. And this is what you have. Let's say, sorry? Okay, so what he asks is, let's say that we have a network and they use some algorithm for some servers and some algorithms for other servers. So what is the algorithm that the tool will select? Well, the tool will select the target algorithms by looking at the IPv6 addresses of the domain that you specified. Sorry? No, so it analyzes the pattern of all of the addresses. Yeah, if they are different, it targets different patterns. So let's say, for example, that the domain name www.freebsd.org uses low byte addresses and also addresses that employ IPv4 addresses. So first address is of one type, the second of the other type. Well, the tool will target both, okay? Let's take a look at another one. This looks like low byte, okay? Facebook, let's see. Two. Yeah, that's true. I should check when. I mean, I should check. So what he's saying is that, you know, for Facebook, the address was, well, Facebook written down in hexadecimal. I should check. You know, I should go back and check where that address was being used. Maybe it could also be the case. I mean, I'm just guessing that, you know, the tool is not able to figure out that that's like a word. So from the point of view of the tool, it's like a random address. And when the tool is not able to identify the type of address, it tries low byte, because that's the most common one. Okay. Now, this is something that is, to some extent, I mean, it's just a couple of slides. It's kind of like related, you know, to network reconnaissance. The title is host tracking, and it's quite related to what we you know, talked before about the privacy implications of including a MAC address in the interface ID. So let's consider this scenario. I have a host that configures this address when it connects to this network, okay? Let's say, for example, that I'm running some kind of server, like a web server. I get a connection from this IPv6 address. Now, the same node that moves to a different place, like a different network. And now that node connects to me with this other address. If I look at the interface ID, and I figure out that this is a MAC address, you see the FFFE, for example, then I know that the value here is a value that is globally unique. If it's globally unique, I can tell that this system is the same one as this other system. And somehow, I can track the system in the network. Let's make a more concrete example. Let's say that I know some guy that I've been, let's say that at some point in time, I've been to a conference with some guy, okay? And I know the MAC address of the guy. And let's say that the conference network has IPv6 enabled. Now, the guy told me that he would be attending the conference again, and I know that he is going to be using his laptop. And I want to check if the guy is there or not. I mean, the guy is not going to tell, obviously. So what do you do? Well, first of all, you learn the well, you know the address, you know the MAC address of the guy. You know the prefix that the conference is using for the network. So what you just do is you put together the prefix with the MAC address, and you ping that address. If that address is responding, then that means that the guy is there, okay? This can have, like, you know, let's say unexpected consequences, because in the same way that here is network 1 and network 2, you could have told something, someone, whoever that is, family, girlfriend, boyfriend, boss, whoever that is, that you were going to go for a business meeting at, I don't know, Romania, right? And you send an email, and in the email header, you get the IPv6 address. Now, the prefix is a prefix that is employed in Hawaii. That's not nice, right? Because it's like your identity is being leaked by the, you know, MAC address, which you are advertising to everyone because this number is unique. Now, the Scan6 tool has a similar example is that if you have a number of, let's say that you have, let's say, one guy that you want to track, and you have, let's say, a number of possible places where the guy could be. Like, he could be at his office, at the, let's say, at the network, or, you know, the coffee store that he usually goes to, so you have a number of options. You could run the tool like this. So this is the more automatic way. In this file, you specify all the prefixes, like networks to which the guy might connect. Here, the interface IDs. This is if you are tracking multiple people, okay? So let's say I have a list of all of your MAC addresses, okay? And I know that you can be here at some university or in a few other places. So I run the tool like this. And what does the tool do? It combines each of the interface IDs with each of the prefixes. And it pings all of the combinations. And when you run the tool, you can tell the tool to print on the screen like a timestamp of when the tool found, that address to be alive. So I could keep this running like forever. And I keep a log of where your system appeared in this or that network, okay? And this is not, this is something that is quite doable. Like, I know people that, usually they are at home, at university, or at this other place. And, from the IPv4 mindset, well, first of all, this cannot be done because usually you're behind the NAT. So you don't get the proof packets. You are kind of like protected, if you want. But with IPv6, this comes like unexpected. Well, why? Because now you have unique addresses for each node. That's one option. Second, because the standard wasn't that good from a privacy point of view. So this is something that is not nice at all. From the point of view of network reconnaissance, because these examples were just like tracking people, if you want. But from the point of view of network reconnaissance, you could say that, let's say you found some kind of target, and it's a target that can move from one place to another. Well, in this case, this Scan6 tool makes it easy to find the target when the target moves from one place to another. You found the target at some specific network. Now, if you know that if this target is like a mobile node, and you know what are the places where this device might possibly move, you can track this device across networks. Oops.
Здесь как раз прошу прощения, на центральной площади, где, собственно, через 1,5 часа начнется церемония награждения, подведения итогов конкурсов «Взломанное будущее».
Okay, so this was scanning. Now, I typically follow, the IPv6 stuff is what I've been doing most of the time for the last, let's say, 7 years. So when it comes to much of the other security stuff, I don't pay that much attention, but I follow everything that is related to IPv6. If you look at the work that has been done in, let's say, related to IPv6 security, much of it has been around extension headers. So if you Google for IPv6 security, it's quite likely that you will find something related with extension headers. Now, let's go back to the IPv6 packet format, okay? I was saying that if you look at an IPv6 packet, you have a fixed header, possible optional headers in between, and then you have the actual payload, okay? Now, in theory, this is supposed to be very flexible. This allows for flexibility because now I can add as many options as I want. I don't have a limit like, 48 bytes of options or 60 bytes of options. If I want to use like, 1,000 bytes of options, it's possible to do it. But there's a problem with that. If you look at, in theory, not in practice, IPv4 routers, for example, or in the network, routers just look at the IPv6 header. They don't look at the payload, okay? A router, in principle, is just a device that only cares about IP, not about what's on top of IP. Now, in the real world, it's usually the case that you have devices that have to do different kinds of filtering, for example. You might have a router that, is enforcing ACLs. Like it blocks packets that go to port 80 because maybe your network doesn't support port 80, okay? Now, what happens if you get a packet like this and you need to figure out what's the port number that is being employed? Exactly. You have to jump over all these headers. Now, what looked like a very cool and nice and flexible idea is not that nice. Why? First of all, there are many router architectures that when they get a packet like this, they process the packet in software. So if you get a normal packet, just IPv6 header and a payload, they forward the packet on the fast path, like in hardware. Packets go like very fast, no problem. If they get a funny packet like this one, the processing of this packet is so complex that it's not implemented in hardware. So they send it to the CPU. Now, now you change it from processing packets on a fast path in hardware versus processing a packet in software in a slow path. Now, obviously using the CPU takes a lot of resources. And if you are an attacker, what you could use this for? Well, man, the first and obvious option, denial of service. If I know that it takes you a lot of work to actually process this packet, I don't send you just one. I mean, obviously, I send as many packets as possible. And when you try to process this, you cannot just keep up. Okay? So that's one of the options. There's another thing, and this is this talks about, let's say, you could say stupid implementations. There are some firewalling devices, even the ACL stuff that you can implement with some routers, that when you tell the device to filter packets, for example, send to TCP port 80, they just look here if the type of the header that follows is TCP. If it's not, they say, okay, this is not TCP, so I can pass the packet. Which is obviously stupid, because what you do as an attacker, well, you put an option here that is not useful for anything, just to confuse the device that is, filtering packets. So you put options. In practice, you don't get anything done with this, just to confuse the device that is filtering the packets. The device look at this, it says, no, that's not TCP, I can let these packets through. But now, thanks to putting these extension headers, you have been able to bypass the filtering rules of the network. That's very typical. Yeah, well, yeah. Sorry? Yeah. I mean, I don't care. I mean, I don't care about vendors. So I can give you like, for example, there's this applies to layer 2 security. Cisco has a device that's called Router Advertisement Guard, okay? This device essentially works like this. You have a switch, layer 2, and you say, well, I want, or let's put things this way. I have a layer 2 network, local network segment. And among the possible attacks, I could have an attacker that connects to that network and pretends that he's a DHCP server, okay? So whenever he sees a DHCP request, he sends a DHCP response, so that he gets all the packets, like he performs a man in the middle. This device, Router Advertisement Guard, what it tries to do is block the DHCP server packets at layer 2. So at the switch, when it sees the packet, I mean, stupidly enough, it checks here if what follows is UDP. And if what follows is UDP, it checks the port number. If the port number is the DHCP server port, it blocks the packet. Now, what happens if you put a destination options? That does nothing, like no operation here. The device thinks that that's not the DHCP and lets the packet through. Yeah. So I was once at the conference. I mean, I had already tried this. And, I was curious. For example, like conference like this too. I mean, lots of people connected. I have no idea. I haven't tried anything. I don't know what's the, let's say, the architecture of the network. But obviously, for obvious reason, I wouldn't be surprised if you have like large network segments. I mean, there's so many people. You cannot have like one segment for each people. So I was once at the conference in Brazil. They were like easily like 2,000 people, easily. And I asked the administrator, like, what do you use to protect, the system from like layer 2 attacks, like the HCP server and so on? We use Router Advertisement Guard. And I tell the guy, well, if a guy sends this, you are screwed. And actually, the proof for this was actually worse. Like 6-7 years ago, I had presented this at the conference in Mexico, and there was a guy very pro IPv6 that, usually pro IPv6 people is like they will neglect everything that is security problems or problems with IPv6. Me, I don't care. I mean, if it's good, if it's bad, I don't care. If you deploy it or not, I don't care. So I do this presentation, and this guy says, that doesn't work because the device that we have blocks it and blah, 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 blah. So the next day, I mean, I was working on the tool, so we got with a bunch of people to a different room next to the main conference room, and I didn't do it on purpose. The tool was just didn't have that many options. So I sent like a DHCP packet, it's router advertisement, strictly speaking, on the network with this. So if the guy was right, the packet was going to be dropped. If the guy wasn't right, actually this was going to be received by all of the people in the conference. Every people was going to configure an address that was invalid. Well, the moral of the story is that for the rest of the day, there was no IPv6 anymore. Or what is worse, I mean, they configured an address that was incorrect, and it was impossible to actually get rid of that. So this is quite useful for bypassing security controls, okay? At least in theory, at least when you are, let's say, within a network. I mean, I don't know what they use here, but in the event that they were using, for example, router advertisement guard, even when they don't have V6 connectivity, let's say if I was, let's say, managing this network, I'll say, if we are not using IPv6, at least block it, okay? So it would be quite likely that they are blocking those packets. But if you send something with this, the packet goes through. If they are using Cisco's router advertisement guard, you can bypass Cisco router advertisement guard with this. I mean, you can try it. I mean, once we finish with this, we can try it if you want. So that's the theory. As I said before, in practice, there are some problems with the extension headers. One of the problems is what I said about performance. There's another problem. And this is something that escapes me a little bit, but I did talk, I mean, I don't, my daily job is not, building routers, but I do talk with people that, have the job of building routers. So these people tell me that the architecture of many routers work like this. You receive a packet, and the first X bytes, some number of bytes, are copied to a very fast memory. Depending on the system, it might be 64 bytes, 128 bytes, usually no more than 256 bytes. Now, the idea is that you copy the first chunk of the packet there under the assumption that everything that you need to process the packet is there. Yeah, exactly. So in theory, that's correct. Now, if the attacker knows that, well, that's quite easy. If I know that your filtering device can only process the first 64 bytes, well, I'm not going to put you the information that you want in the first 64 bytes. Actually, I put a lot of crap so that you don't have the memory to actually copy all my extension headers. So in your fast memory, the only part that you put, if I go back to the packet, is this. Maybe this is just already like 256 bytes. Now your router receives this. You have two options. Option one, if you cannot know for sure what's inside the packet, you just drop it. But you might be dropping legitimate stuff. Option two, you let it through. Now many people let the packets through if they cannot see what's on top. This means that if you include many extension headers in here, or at least one that is big enough, in the case of many networks, you will bypass the security controls. Why? Because the device that they are using to enforce filtering rules is not able to look inside the packet. It cannot get so deep as here, okay? Well, that's true. Now what happens is that let's say that, I mean, if you're using, or let's say if it's a router that you are using just for at your home, you could do it. Like, you say, okay, if I don't get the full packet, let's process, but slow. Now, if you're operating the router of a carrier that, carries lots of gigabytes of traffic, then doing stuff slow is not an option. You either do it fast or you don't do it. So what many of these people do is, if I can do it fast, I'll process it. If I had to do it slow, I'll drop it. So obviously what I recommend is drop it. That's the reason for which you might expect, oh, thank you. I was dying. That's the reason for which you might expect that in the real internet, like, the real IPv6 internet, these packets probably don't have a very, let's say, good time or a very fun time. Now, years ago, at the ITF. ITF is, the standards organization that writes the specifications for protocols. There was some guy that was saying, well, I know that fragments are dropped quite a lot on the internet. But, that's like real life. Like, people talk about a lot of things, and you never know who was the guy that said it for the first time. But you repeat it. Like, somebody says that fragments are dropped, and then you repeat, well, yeah, I hear at the conference that fragments are dropped. And then eventually there's lots of people, repeating something that nobody knows if anyone checked that, but they repeat it anyway. So nobody was showing actual data about the drop rate of these packets. So I said, well, let's try to measure that, because maybe it's bullshit, maybe it's not, maybe they are dropped, maybe they are not. So I decided to, come up with to produce a tool to actually test whether the packets were being dropped or not. So the first very basic test that I did was essentially kind of like implement like a ping tool with the support for extension headers. Okay? If you just use the regular ping, you cannot tell ping to use extension headers. So it's not possible to try anything. Now, I did like my own version of ping with support for extension headers. And I measured the drop rate for those packets. Now, the numbers were horrible. Like, horrible. And, I said, well, maybe there's a problem with the tool, or maybe, many things could be going on. So I said, it's better if rather than simply running ping, which tells you, if packets go back and forth or not, better to use something like traceroute, because traceroute will tell you until which point the packets get. So I looked at the popular or open versions of traceroute, which are like 3 or 4 of them. Like, if you look at Linux, BSDs, and so on, all of them use, there are 3 or 4 versions of it. But nobody of them was using extension headers. So nobody of those implementations would allow you to put extension headers in the packets. So I had to come up with my own version of traceroute, so to speak. I mean, the name is different. It's called Path 6, not because the name is great, but actually all the other names were already used. Trace, trace RT, traceroute, blah, blah, blah. So I did the measurements, and this is what I found, okay? These initial measurements, I tried to do, so there are like different combinations of things here. First of all, and with the same set of addresses that I had before, remember, web servers, name servers, and mail servers, I was measuring whether 3 different types of extension headers were working or not. So the different extension headers are, these ones in blue, destination options. These are extension headers that, in theory, are only processed by the final destination, okay? These are, among the possible extension headers, the ones that are more like, okay, if you want. Option 2, in red, hop-by-hop options. These are horrible, because these extension headers have to be processed by every single router. I mean, the most sane thing that you can do is drop packets that have this. This means that every packet that gets to process, or every router that gets to receive a packet with hop-by-hop options has to process the packet in software. That's like completely insane. Third option is a fragmentation header. You might remember that when we started, with this workshop, I said that the basic support for fragmentation was removed from the base header. And if you wanted to fragment a packet, you had to do the fragmentation using options. Well, the options are a fragment header. So essentially, it's an optional header that has the necessary information, fragment ID and all of that. Now, what did I do? I ran traceroute, employing these extension headers to web servers, mail servers, and name servers. This is the drop rate. This means that 10% of the packets, or let's put things this way, if you send packets with destination options of 8 bytes, 10% of them get dropped. That's quite large already. Like 10% drop rate is quite large. For hop by hop, is 40%. That's kind of like half of the packets here. Not to mention here that it's over 50. For fragmentation, you get between something like 30 and over 50%. Now, you might say, well, for web servers, I don't care, because it's, the web uses TCP, so you're not supposed to use fragmentation there. Mail servers, it employs TCP. You're not supposed to be using fragmentation there. But name servers, It uses UDP, so you need fragments. And you get a 50% drop rate. Now my guesswork, and this guesswork can be easily confused with possible bullshit, right? Is that, yeah, this number, these results are horrible, but what happens is that nowadays you still have IPv4. So probably, when you need to contact a name server, the name server is, if it's available on IPv6, it's certainly available in IPv4 too. So maybe when you try to contact it with IPv6, if it employs fragmentation, the fragments get dropped. So eventually, IPv4 is tried after that, and IPv4 succeeds. That's what I think. It's guesswork, right? It's not the, it's, let's say, probably this could be subject of, further study. Now, there's another thing. I presented this at the IETF, and the ballots were like flowing like this. Because, this is like saying, well, this shiny, great thing that you produce in the real world, it doesn't work, okay? And people don't like that. I don't care, but people don't like that. So there were like lots of objections, like that. And then a guy said, well, but where in the network are these packets drop? Because he said, you can divide the internet like in autonomous systems, right? Like autonomous systems is, well, autonomous system. So what this guy said was something like this, which in a sense makes sense. He says, if the system that drops these packets is in the final autonomous system, or to put it in a different way, if the guys dropping the packets are the same guys to which you are sending the packets, then it's okay. They know what traffic they want to receive and what not. The real problem is when the packets are filtered in the middle of the network. It's like I'm trying to send packets with extension headers to him, and the packets have to go through him. And he's the one that decides that he don't want those packets. So he doesn't even get aware about that. The decision is not taken by the guy that is willing to receive the packets, but somebody else. So this is the rate, or what this slide tries to, illustrate, is when packets are dropped, what percentage of those packets are dropped by an autonomous system different than the last one, different than the destination, I guess. So what you see here is that between 30 to 60%, the drops occur not at the final AS, not at the final autonomous system, but in the middle of the network. This means I want to send packets to him, but it's not him that drops the packets. It's someone in between. So maybe even if he wants to receive those packets, he can't. Because somebody in the middle says, you know what, I'm not going to deal with those packets. And that's something that, is going on right now. So what does this all mean? Well, yeah, there are two different ways to read this. Obviously, one way to read this is that if you want to use or employ extension headers for legitimate purposes, you're going to have a hard time, okay? Because at least in the public internet, they get dropped a lot. Now, the other thing is that, a lot of the work that I was telling you that much of the stuff that has been done, not by me, but by other people in the area of IPv6 security, has to do with extension headers. So there are many people that say, well, I found that I can evade snort if I put an extension here and there. You have like so many papers about that. I know that I can evade this or that firewall if I put an extension header this or there. Lots of papers about that. Now, can you really use that in practice? Well, it depends. Why? If you are connected to a network, like, you are connected to this network, and some systems, you have some system enforcing like filtering policy, and you can, let's say, fool the system with extension headers, that's perfect. Now, given the drop rates that I showed before, given this, if you are trying to attack a remote system, well, probably it's not a good idea to put extension headers. Why? Because you are really increasing the chances that your attack packets are dropped in the middle of the network. So you were expecting to, circumvent or fool the security controls, but since there are systems in between the network that, they simply drop these packets, as soon as you put extension headers, you're actually shooting yourself. It's like you're making your own attack packets get dropped in the network, okay? So,
the technical part of the form.
as I said, this, in order to produce these measurements, I had to, implement my own version of traceroute.
Section phishing
The tool is path 6. It's supposed to be a traceroute for IPv6 with support of extension headers. The tool is kind of like quite simple and flexible too. Flexible because you can essentially use any protocol that you can or that you want for the proof packets. The proof packets can be SYN packets, they can be ICMP packets, they can be UDP packets. You can select whatever port you want. You can select the TCP flags as you wish. Typically with traceroute, you cannot do that. And for example, there could be cases like if your traceroute implementation employs ICMP for the proofs, maybe some system in between is dropping them. But if you use TCP instead, maybe the packets get through. So that's one of the features of the tool. The other feature is obviously extension headers. So this option means that you are including a destination options of 100 bytes. Okay? So IPv6 header, then destination options of 100 bytes, and then, well, this is the destination, and then the payload. Okay? Now let's try that and see how it works. Let's see. Sorry? Yeah. Yeah. So this is kind of like traceroute, right? List of IPv6 addresses, you get to find a destination. So no problem here. Now, let's do this. Destination options of 100 bytes. Packets get this far. What's going on? Well, until this guy is okay with extension headers. After that, there's a guy that don't like them, throw them away. Now, obviously, this is what I was telling you about the implications. You might read papers that say, well, I can evade Node by using extension headers. Well, if you get there. Now, if I was trying to, let's say, attack Google in this case, well, I don't get past the 4th router, and there were like 15 routers. So my packets die like very close to me because there's a system that is dropping them. Sorry? You know what you have. So what you're asking if the packets should be allowed to get to the final destination? Yeah. Yeah. Yes, exactly. So what he's asking, he's saying, does the IPv6 standard require that these packets actually get to the destination? Yeah, that's what the standard requires. But that's why I said that, the standard is unrealistic in that sense. I mean, in theory, yes, but in practice, and there's a reason for that. I mean, there might be people that they drop these packets because they are just idiots. That's an option, okay? But there's people, I mean, idiots are everywhere, but there are also valid reasons for actually dropping them. And it's quite simple. Most networks need to enforce ACLs. If you want to enforce ACLs, you need to know what's the upper protocol. Now, if the packets have extension headers, you might be unable to get to the layer 4 information or have to do it in the slow path, very CPU intensive. That's not an option. So obviously, if that opens the potential for the denial of service, you better drop this. Huh? Well, yeah. Well, the thing is, let's put things this way. Is what they say, about the difference between theory and practice. So the standard says you shouldn't look past the IPv6 header. Well, in theory, okay. because the network should be transparent and blah, blah, blah. Well, in the real world, there are firewalls. In the real world, every system that needs to enforce ACLs, they have to look at layer 4. That's the way life is. So you have two options. Like, be stubborn with your, you don't have to look farther into the packet, or do something more sensitive. And there's another thing, like, like everything. Yeah, well, I mean, it could be, in any case, unfortunately, the B6 standard is being moved. So in the ITF, you have like different, let's say, maturity levels for standards. IPv6 was in, I think it was proposed standard, which is like almost the final step. Now, right now, it's being moved to full standard, which means like it's supposed to be mature and blah, 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 and they are keeping it this way. So there's a big difference between what the standard expects and what happens in the real world. Now, besides security, there are like, practical operational implications of this. Let's say that you are a guy that is developing a protocol. And let's say that somehow your protocol needs options. Would you use extension headers? No. Why? Because they don't work. You cannot rely on them, because if you use them, your packets will get dropped. Now, that also gives the reason for people blocking them, because I'm an operator and say, with these packets with extension headers, there could be the potential for denial of service, for blah, 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 blah. Are they used for anything useful? No. Then why should I, deal with the potential problem if there's no real use for them? So it's like a chicken and egg problem. You're not going to use them because they get dropped, and they get dropped because they are not used. So I don't think it's hard to imagine, like, things are going to improve a lot. So this is the option. This is another example. Well, you can, if you look at the manual page, it lets you specify TCP flags, what's the protocol that you want to use, port numbers, anything. Now, usually, let's say that you are an operator. In this case, you are doing network reconnaissance. And you want to be able to tell what's the system that is dropping the packets, okay? But you don't want to, one option is just run traceroute, okay? Look, first of all, run traceroute without extension headers, see if the packets get to the final destination. Then you run traceroute with extension headers, and then you compare the two traceroutes and you try to figure out what's the system. Now, I did a tool that does exactly that automatically. So you don't see what the tool is doing, but essentially the tool uses the traceroute to try to find that out. Let's see. Let's see if it works. So this is a different tool. Let's see if it's right. Oh. This is a different tool. What it does, it says, I want to try packets to, well, in that case, Google, www.google.com, with a destination options header of 8 bytes. Okay? So I'll tell you what the tool did, because it just prints the result and you say, what the hell did the tool do? First of all, it did traceroute without extension headers. We want to know if it's possible to get to the final destination. Second, we do traceroute with extension headers. And if the packets don't get to the final destination, we just compare the two traceroutes and find what's the system that is dropping them. And when we find the IP address that is dropping the packets, we use Whois to actually look up what's the organization that is dropping the packets. In this case, it tells you that the drop-in node is this one, the router with this IPv6 address that corresponds to Google. And this is actually that, I know that it's real. I mean, at times the tool can, tell you that it's one organization, but the real one is another one. But Google, by policy, they drop all IPv6 packets that employ extension headers as soon as they get to their network. So that's the official policy by Google. So packets that contain extension headers are dropped. In the event that you never, employ these autonomous system numbers, these obviously identify the organizations that are supposed to be managing these routers. So let's say that you wanted to use extension headers, and you say, I want to complain to these people because they are dropping these packets. Well, you go to Whois, look up this number, and you get the contact details. They are probably going to tell you that they will not change anything, but at least you know who you have to call. So this would be like the methodology, right? So I showed the Black Hole 6 tool, but it did all the magic, behind the scenes. So first of all, this is how the Black Hole 6 tool works. First of all, you run traceroute without extension headers. You try to get, for example, to this system and packets get there. Now you run traceroute with extension headers. And the last system that responds is this one. Then you assume that this one is the one dropping the packets. Okay? I mean, obviously, we are assuming, which is what happens in most of the cases, that all this list of systems is the same as this one. I mean, most of the time, that's the case. It could also happen that packets go through different routes, and in that case, obviously, the tool will fail, because one probe and the other is following different paths. But if in both cases the route is exactly the same, the list of systems is the same, then you can tell what's the system that dropped the packets. Well, this is details. This is not that important, but essentially, what the tool tries to figure out is or try to analyze. When it tries to analyze what's the autonomous system, you have to consider a number of options. There are cases in which you have, for example, like 2 peering systems here, and this system is the one that provides the address space for the peering session. You also have cases in which the address space is provided by, this AS. So that's the reason for which there are some specific cases where the tool might be ambiguous. It tells you, I cannot determine exactly if it's this autonomous system or this other one, the one dropping the packets. So it can tell you what's the IP address, but it cannot tell you to which AS that IP address corresponds. Oh, thank you. Port scanning. To make the story short, I mean, we're going through it, but to make the story short, obviously, I would say that except for the fun of implementing a port scanner, I mean, you'd use Nmap, okay? It's complete, it works quite well, you are used to it, blah, 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 blah. There's 2 reasons for which I implemented a port scanner myself. One, in part, was for the fun of it. I had never done it, so I wanted to do it just once. And then a more realistic reason, was that Nmap doesn't have support for extension headers, okay? So, I mean, if you're going to do the same thing as Nmap, there's no point. I mean, everyone uses Nmap, everyone is used to Nmap, so doing the same thing as them, if you're going to do the same or not as good as them, don't. But if you can do it better, let's say faster, or you can do something that they don't do, let's say you might have 2 minutes of fame over there. I mean, eventually they will going to implement it, and your tool is not going to be used by anyone. But let's say for a couple of months, you could say that your tool is useful. That's the idea. So essentially I implemented like the same scan6 tool that we were employing for address scans. It can implement port scanning. So obviously you can similar. I think it's kind of like the same syntax as Nmap or similar. So you specify this option, which is a port scan. You specify the protocol number, and then you specify a range of ports. Okay. Then you can specify the scan type. Like, you know, for TCP, there are like different, let's say, scanning techniques in principle. I think I had a, oops. Okay. Okay. So I'm going to go through this more, let's say, a little bit fast for two reasons. First of all, it's kind of like late. The other one is that usually the only people that like TCP is the people that work on TCP. So it's like when you start talking about, you know, three-way handshake and so on, that's the place. If there's people that are still awake, that's where everyone falls asleep. So I'm trying to, you know, to avoid that from happening. This is a normal three-way handshake, or in TCP, meaning that when you establish a TCP connection, you need to exchange 3 packets, okay? Now, there are different scanning techniques. The more basic, if you want, is what is called the connect scan. Connect scan is about doing a full three-way handshake, okay? It's like really able if you want, but it takes longer time. And you could also say that, you know, it's easier to track the attacker to some extent too. Then there is the SYN scan. This is the more usual one. SYN scan, you don't do a full three-way handshake. You just send a SYN packet. If the port is open, you get a SYN-ACK. If the port is closed, you get a reset, and that's it. But you don't try to get the full TCP connection. This one we implement. And then you have this other technique, which essentially they are all the same. FIN, null, and Christmas. Essentially, you send a packet that doesn't have the ACK bit set and wait for a response. If you get the reset, the port is closed. If you get a timeout, the port is open. Problem with this scanning technique is that it's way slower than, for example, the SYN scan. Now, one thing that you typically, I mean, before doing kind of like security stuff, I used to do a lot of TCP stuff. The working group at the IETF that I was mostly contributing to was TCPM. So that's why, you know, I kind of like enjoy this stuff. But these are just specifics. So let's say that you could live like a perfect life without knowing the internals of what's going on here. Another thing that I implemented, this is like a total ripoff of Nmap, is the option to scan for the most frequently open ports. So essentially somebody, I think was Fyodor from Nmap, he scanned the whole internet and he published like stats about what are the port numbers that are more frequently open, okay? So if you want to, you know, if you don't want to scan for all of the possible open ports, like, you know, from, let's say, 1 till 65,000, blah, 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 then you scan for, obviously, 80, let's say, 443, and the most usual ones. So you can run the tool like this. This is like all the port numbers that were, you know, found open when this study was done. Or you can say, well, I want to target only the, let's say, the 10 top port numbers. The tool implements this stuff too. Okay. Obviously, all of this stuff that we have seen here is stuff that Nmap implements. So you say, why the hell should I learn the syntax of your tool if I can do it with Nmap? I mean, in reality, I don't know if you should, but let's say if you want me to give you a reason, you can use extension headers here. So if you have a scenario, for example, in which by using extension headers, you can circumvent a security control, well, that's the case in which you'd use this. Because you can do a port scan that if you do it without extension headers, your packets get blocked. If you put extension headers, your packets get through. Now, this is kind of, I mean, if you don't, let's say, follow the entire explanation of this technique, don't worry, because for so many reasons you don't have to worry. But it's interesting, so that's why I included it here. So I don't know if you remember from the IPv4 times. This was like, I think it was late 90s. The guy was Salvatore something, guy from Italy. Salvatore, I don't remember the name, Salvatore something. So he essentially published a technique called dump scan or idle scan, which essentially allows you to port scan a system without having to send packets yourself to that target system. So let's first of all, let's see, okay. Let's first of all try to see the two scenarios. I'm going to do this very fast because this is really boring. We have these two scenarios. This is a scenario for an open port. This is a scenario for a closed port. So in the case of an open port, I send a SYN packet. This system responds with a SYNAC. I respond with an ACK. Closed port, I send a SYN. I get a reset in response. Okay? Now let's assume that this SYN packet has a spoof IPv6, a spoof address. Doesn't mean if it's IPv6 or IPv4. It would be something like this, okay? I'm sending the packet from here. I'm the attacker, okay? But I'm using the IP address of the zombie as the source address, okay? I'm spoofing the address, so I'm not using my real address. Now, let's analyze what happens in the case of an open port. I send the SYN packet, and the victim, the target of the port scan, responds with the SYNAC. But since the address was spoofed, it wasn't really my address, the address of the attacker, obviously the packet goes to the zombie. That was the source address of the packet, okay? So I send a spoof packet using this guy's IPv6 IP address, okay? The packet gets here, the victim responds to the address that was in the SYN segment. Now, when the zombie receives the SYNAC, says, well, this SYNAC is for something that I never sent. So this doesn't make any sense at all. So it responds with a reset. Okay? Let's see what happens in the case of a closed port. You send a SYN packet. The victim responds with a reset because the port is closed. Where is this reset sent to? Obviously to the zombie. Now, in this case, the TCP processing rules say that if you receive a reset, you don't respond with a reset, for obvious reasons. Because if you respond with resets, there could be a scenario in which we are responding to each other, and you know that never stops, okay? Now, if you look at these, let's say, these two scenarios, you could say, okay, I send the packet with an address that wasn't my address. So the victim never saw my address, never, because I never used it. What's the difference between, or what's one of the difference between these two scenarios? Well, when the port is open, the zombie sends a packet. When the port is closed, the zombie doesn't send any packet. Now, obviously, the question here is, if somehow I could do something to tell if the zombie is sending a packet or not, then essentially I could know whether the port is open or closed, okay? So I have to do some magic in here to be able to tell whether the zombie transmitted a packet. Obviously, I have to do some kind of magic because I don't see this packet. It's sent from the zombie to the victim. I don't get anything from the zombie that tells me whether he sent, the packet or not. How do you do this? And this is how, let's say, how you do this in the IPv4 world, okay? In IPv4, all packets contain a fragment ID, okay? And many implementations, they use predictable values for the fragment ID, a counter, okay? So every packet that they send, for example, if the first packet had a fragment ID of 1, the second has a fragment ID of 2, the third a fragment ID of 3, and so on, okay? So let's see what we could do. I mean, for the time being, let's assume that this is IPv4, okay? Because it says some CMP version 6, but let's assume for a second that this is IPv4. First of all, I send the proof packet to the zombie. I get a response from the zombie. And what I do is I record the IPv6 fragment, the fragment ID that is in the packet. For example, it could be 45,000, any number, doesn't matter what's the specific number. Now, the next thing I do is I send the SYN packet, the files, the spoof packet. The victim responds with a SYNAC because the port was open. Then the zombie responded with a reset. Now, if the zombie is employing predictable fragment IDs, it used 45,000 for this one. Then it might use 45,001 for this one. So then, if I send a proof packet and the zombie responds, well, if one packet was transmitted, like in this case, I get 45,002. So by comparing, by sampling the first fragment ID, then sending the spoof proof, and then sampling the fragment ID again, then I can tell if the zombie sent a packet or not, okay? Obviously, you could say, well, this system shouldn't probably be using predictable fragment IDs. Well, go and tell Microsoft. I mean, they do, okay? What happens in the other case? Close port. I send the packet, I get the response, let's say fragment ID 45,000. I send the SYN packet, I get the reset, the zombie gets a reset, and it doesn't transmit anything. When I sample the fragment ID again, I get 45,001. Okay? Now, obviously, this is the next consecutive number to the original proof. This means that between this proof and this other proof, nothing was sent. So that means that the port was closed. And this is actually implemented like in Nmap for IPv4 already. If you ask me, I think that this is like a cool technique, you could say. Whether I would use it or not, I don't know, probably not. Sorry? But let's say my take, or the reason for which I said, is like, I mean, you could say, well, I don't want the victim to know my identity. Well, I just go to Starbucks. I mean, I use my own IP address and never go there anymore. Sorry? Yeah. That's true. What I'm saying is that for the purpose of just getting the result of whether, you are, for just the purpose of scanning the ports, I would say that, I mean, there are many things like you could do. One thing is just use some system that you don't care about. Another thing is use what is usually called decoy traffic. So other than the traffic that you really need to do the scanning, you send some, crap so that you confuse the guys that are receiving the packet. So they don't know whether what they got is actually the legitimate packet that you are using or it's something else. Now, there's a problem. Years ago, that was like 7 years ago, I was teaching a B6 training course, and the day before I was finishing slides, and I came up with this, and I said, well, I mean, it's kind of like okay, but there's a problem. In IPv4, you have the fragment ID in every packet. Now in IPv6, you don't. So the thing is that you can do this in IPv4 because there's a fragment ID in every packet. In IPv6, you could do this part and this part. For example, I send a ping packet that has to be fragmented. So obviously, if the query was fragmented, then the response is going to be fragmented too. So it's possible to sample the fragment ID here. It's possible to fragment the fragment ID here. The problem is how you make the zombie, put a fragment header for this packet. Sequence number, you mean? Okay. Oh, I haven't checked that. But I was trying to, let's say, reproduce this with the fragment IDs. And I say, well, how do I make this packet use, one number from the fragment ID space? Then I went back to reading the core IPv6 protocol specification. And when I'm going through the standard, there's something that is like completely insane. I mean, the reasons are long and they don't matter, but it's insane. And there's a part of the standard that says, if you receive a ICMP packet-to-big message, packet-to-big is like fragmentation needed by the F bit set in IPv4. Essentially, it's a packet that tells you, you're sending packets that are too large, you should reduce the size of your packets, okay? Now, the standard says, if you receive a packet, an ICMP packet-to-big message, and the packet tells you that the MTU, let's say the size of the link, is smaller than 1280, this is like the minimum IPv6 MTU. So if there's an IPv6 link, it's supposed to be able to handle MTUs of this size or larger, okay? Now, standard says, if you receive one of these messages that claims that the MTU is smaller, you don't need to reduce the size of the packet, but from that moment on, you have to include the fragment header in all of your packets. And I said, no, that cannot be possible. That's like insane. So I was with one of the guys that was attending the training. I mean, the guy was like, he knew a lot of stuff. So he was using, I don't know if it was Scapy, for, crafting packets. So he did the tool to actually spoof this packet. So we tried that. And actually it works. So the scenario that you have is this. This is like a complete implementation. First of all, you send from the attacker to the zombie an ICMP packet, and you use the source address of the victim. So this is like, this packet is really meaning like the victim is telling the zombie, please send me all your future packets with a fragment header. And obviously, if you send all your packets with a fragment header, you are going to be using, a fragment ID. Now, as a result of this packet, now every packet that the zombie sends to the victim is going to use, it's going to use a fragmentation header, and then it's going to use a fragment number. So after this, I sample the fragment ID, I get this value, I send the spoof SYN packet to here, victim responds with a SYNAC, and when the zombie responds with a reset, because of this ICMP that it had got before, it sends the reset using a fragment header. It's totally insane, but that's what happens. So now, if this packet was sent, one of the numbers from the fragment ID space is going to be consumed. So 45,000 here, 45,002. Obviously, for this case, it doesn't matter because the zombie doesn't send anything. And it actually works. This is, I don't have a, you could use like with Windows. I forgot to include the command line, but Nmap implements this for IPv6 already. I don't remember if you look for Nmap IPv6 idle scan, it's implemented with the scripts. With the Nmap scripts? It's called scripts, right? And this is the guy that implemented that, a guy from Germany that usually attends IPv6 events. Now, what's the problem with that? No, this is my idea of this idle scan. So, I think it's a cool idea. And even, it's so insane that you spoof an ICMP and that triggers the use of fragmentation. So that's kind of like, very, you could say, sophisticated in a sense, right? So it looks like cool. Now, there are problems with that. First of all, I was saying before that when packets use extension headers, they get dropped a lot. Now, in IPv6, support for fragmentation is with an extension header. What does this mean? Is that if you're trying to scan with this technique a system that is on the public internet, chances are that the packets that employ the extension headers are going to be dropped. So this makes this scanning technique unreliable, meaning as long as you start using extension headers, chances are your packets are going to be dropped. Now there's another thing. Because of other work that I did in this area, which is not described here, but I did other work in this area, these packets, these atomic fragments that we call, these packets that include a fragment header even when even when you don't need them, have a lot of different problems. I published this RFC, which essentially tells you all of the problems that these packets have. And the revised standard for IPv6, which is this document, is going to be published as an RFC soon, removes the support for this functionality. So this means that when the new standard is published, if a system receives one of those ICMPs, this one, it should just ignore it and don't use fragmentation. There are quite a few systems that have already removed that support. They understood the problem and they say, well, those packets are not really useful, so they remove that functionality. So even when the standard has not yet been formally, let's say, updated, there are a bunch of implementations that already say, no, that's insane, we are going to remove. Linux is one example. So Linux was reacting to these packets, but now that has been removed from the kernel. So you cannot trigger, that behavior with Linux anymore. Okay. Couple of comments. I kind of mentioned that in IPv6, the ICMP version 6 is used for a bunch of things, okay? First of all, it's used for some of the same things as in IPv4, like, reporting errors, like port unreachable and all of that. Now, there are two things that are totally new in v6. One is neighbor discovery. Neighbor discovery is essentially ARP, with the only difference that in IPv6 is done with ICMP. Another one is stateless address auto-configuration. This is like, let's say, a cheap version of DHCP, to put it in some way. So with stateless address auto-configuration, the idea is that when you connect to a network, you send an ICMP packet that says, please, routers, give me the configuration information that I need. If there's a router connected, it responds with a message, and it tells you, lots of stuff that you need, including the prefix from which you should configure your address. There are a couple of tools. There are a couple of tools which have functionality that I guess, I was using these tools and I was lazy to implement that myself. But there are two tools of the same package that can be employed to easily play with neighbor discovery. Okay, neighbor discovery and SLAC, stateless address auto configuration. First tool is NDisk6. What is this tool about? It's like sending ARP queries on the local network. So you send a query, you tell the system, please, I want to know what's the MAC address for this address. And then the tool prints the responses that it gets. Okay? So this is just an example. I run the tool in this way. The tool says, okay, I'm asking for this address on this interface, and this is the response that I got. This system tells me that the MAC address is this one. Okay? If you ask me, well, is this that useful? To be honest, I haven't used this that much other than for debugging. But again, network reconnaissance is learning stuff about the network. You might find scenarios where this might be useful. There's another one which is maybe more useful, which is a tool for playing with auto-configuration. The tool is quite similar. What the tool does, it sends a router solicitation on whatever interface you specify. So in this case, we send a router solicitation on 8080, and the tool prints the response. And let's look at some of the information that we have here. I mean, I'm not going to explain everything, but because this will be like explaining auto-configuration completely, but some information you can easily understand what it's about. First of all, prefix. The router is telling you that you have to configure addresses from this prefix. Okay? Now, associated with this prefix are two different lifetime values. Valid means that if you don't hear from the router anymore, after this number of seconds, I don't know, it's hours, I don't know how many hours, you should discard this information, okay? Completely discard. You should remove the address that you had configured. Preferred lifetime means that during this amount of time, you can use this information for new communications. Another one, why is that so small? Okay, there's this value that's called router lifetime. Router lifetime means if you don't hear from this router earlier than in 30 seconds, you should completely discard any information that was provided by this router. Typically what happens is that routers send multicast packets very frequently so that this timer never expires, okay? I mean, obviously this talk is about network reconnaissance, but by this description you can probably think of some attacks that you could do. Like you spoof a router advertisement and you specify a router lifetime of 0. What happens after that? All of the local nodes completely discard all the configuration information and you get the denial of service. But that's not the topic of this presentation, okay? But at least, you know, this is a tool that you can use, for example, to learn information about what are the routers in the local network and what's the information that they are advertising. Like, for example, if I send this on, let's say, these 6, so this is what I got, right? This is the prefix that is being advertised. So if you wonder, hey, why when you show the configuration of your system, why was the prefix? Why was that system using the prefix that it was using? Well, because it got this message, you know, and you get all the timers and blah blah blah. Okay. Other messages, these have, let's say, they don't have a lot of use, but they are there. So there are informational messages in, you know, ICMP version 6. One is echo request and response, which obviously I'm not going to explain that. I mean, it's just that they exist in IPv6 in the same way as in IPv4. You can use them for the same things, etc., etc. And there are other ones that are just available on IPv6 and not on IPv4. They are ICMP packets, but of different type. They are called node information query and response. What kind of information you can, request? Let's make it quite simple. You send, for example, a ping packet to the all nodes multicast address, and you get the domain names of the nodes connected to that network. It's in the protocol, so it's not that we're using the DNS to obtain these domain names, okay? You can see that we're using the ping6 tool, but the -w option means that the packets are not ping at all. I mean, the tool is the same, but the packets are node information queries and responses. This is like a virtual network that I have with a bunch of, FreeBSD and OpenBSD and so on. But, it's kind of like curious because in IPv4 you didn't have like a packet that, could get you this kind of information. There's another one, different type. I mean, obviously you can look at the addresses. This essentially means I'm sending a query to all of you asking about what are the addresses that you are employing, okay? So the packet is sent to the, what is it? So in this case, you cannot send the packet to a multicast address, but you have to carry a specific system, okay? I send the query, and what you see in the response is that the system is informing me of the addresses that it's using, even loopback, okay? It just is telling me all of the IPv6 addresses that it has configured. Now, I don't know if there was another one. No. Some, let's say, limitations of this technique. One, at least when it comes to the standard, it can only be employed on a local network. Okay? So you cannot use it across the internet. That's one limitation. The other one is that the only systems that implement this functionality are BSDs and macOS, which is derived from BSD. But I don't remember about Linux. I don't remember about Linux. Windows, certainly, they don't implement this. Let's say the curious part is that I don't know why the response to this packet is enabled by default. First of all, the standard for this protocol was published as an experimental protocol. Experimental means, I was playing with this. I don't know if it's useful. But probably the reason for that was that the same guy that, this is a Japanese guy, Shunichiro, blah, 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 blah. He was the guy that wrote the RFC, and he was the guy writing the IPv6 code. So, you wrote the standards, you don't care. You do it because you can, right? So, but even after, years, the guy even died. Still, even operating systems such as OpenBSD, which are generally, they are, jealous about the information that they disclose and so on, they still support this protocol. I don't think there's any legitimate use for sending this information. Even for, let's say for operation and management, since this protocol is not supported by all of the systems, you cannot rely on this. There's no point in relying on this when, Windows will not respond to it. But it's still there. I was, when we were running the Black Hole 6 tool, the tool was, what's that? When we were running the Black Hole 6 tool, it was informing you about, giving you information about the autonomous system of some IPv6 address, okay? Obviously, I implemented all that in the tool because I needed that information. But let's say that for reasons that, they are your own, you have one IPv6 address, and quickly you want to get information about what's the autonomous system. Well, there's a script in the, in the toolkit, script 6. Script 6 is when there's stuff that, doesn't require its own tool, it ends up here. So you run script 6 with the get AS option, and then specify an IP address, and then the tool provides all the administrative information for, that, for that address. So this is the regional registry that manages this address space, and this is actually the organization to which the address space was assigned, okay? If you ask me why I might want to do this, it depends on the case. But the thing is that the tool is there if you are, searching information about a network or about an IPv6 address. Finally, we go to, I think this is the last topic, and should be because we are kind of close. We are covering DNS for IPv6 network reconnaissance. Obviously, there's a lot of stuff related to the DNS that you already use for IPv4. I'm not going, obviously, to discuss DNS zone transfers. You either know it from before, or if you don't know it, you don't know it. DNS brute forcing, I implemented that in a tool. I don't know why, but it's in the toolkit. I don't know. Maybe I tried to use some other tool. I didn't know which tool, so I ended up implementing it. And there's one specific, let's say, feature of the DNS that, for me, it's probably the most interesting feature of the DNS when it comes to IPv6. And as a personal, let's say, personal disclosure, in the beginning of the workshop, I told you, well, there are these two toolkits. There's one that I authored myself. There's the other one that was authored by this other guy. Well, this is the tool that I envy the most of the other toolkit. So if you say, what is the tool that you want to have and you don't, it is this one. That's why I'm using, for everything else, I'm using my tools. But for this, it's like the tool that this guy implemented. It's great. It's great. So this is brute forcing. Short explanation of brute forcing. There's this script that, let's say you have a text file with a list of domain names, like let's say google.com. Now it's quite likely that if you have a base name such as google.com, it's quite likely that www.google.com exists, and probably ns.google.com, and maybe ftp.google.com. So this tool just, first of all, does the combination of all domain names, and then tries to get IPv6 addresses automatically. So if you wanted to hack, let's say, Toyota.com, you could say, okay, I put Toyota here, and then I try to run the tool like this, and I will try smtp.toyota.com, mail.toyota.com. I mean, you can do it manually, but it's easier if it's in a script. What's that? Well, whatever. This is the part that is actually cool. You might know that, I mean, this is something that is in IPv4. It's not employed for the same thing. But you know that in IPv4, the usual thing that you do is you start with the domain name and you get an IP address. That's the usual thing, right? So you're using a browser, you put google.com, you get the IPv4 address, you know where you have to send your packets. Now, you have other things, and let's do an example. Let's say that I do a trace route. Well, jeez. I'm using Jesus. I was supposed to get names here. Let's say trace route 6, I guess. Well, something is not working as expected, but let's put things this way. Typically, when you run traceroute, you get the name of the system besides the IP address. Okay? I don't know why I'm getting just the IP addresses. Yeah? But typically, when you run traceroute, you get the names. Now, you might wonder, well, how? Yes. You might wonder, well, how do you get the names? Because the usual thing is that start from a name, you get the IP address. But in this case, somehow you are doing the opposite. You start with an IP address, and somehow you get the name. Well, the explanation for that is something called DNS reverse mappings, okay? DNS reverse mappings exist both for IPv4 address space and for the IPv6 address space. The workshop is about IPv6, so that's why we focus on IPv6. Now, you could think of the reverse address mappings as this. If you're assigned a part of the address space, you are responsible for the reverse mappings too. And there's an area of the DNS called IP6.ARPA that is the one that is employed for the reverse mappings. So let's say that you have a complete IPv6 address, you write it backwards, okay? Like this, each of these characters is going to be an hexadecimal digit, because each of the numbers in an IP6 address is an hexadecimal digit. You write it the other way around, and then rather than looking for quite A records, you look for PTR records. PTRs is essentially a domain name, just to put it simple, okay? Now, that part is kind of like okay. I mean, there's nothing, let's say, new about that. You know it from the IPv4 world. Now, there's something quite interesting. When you start searching, obviously, how many, let's say, circles of this you have in the address? So let's say if I put the full IPv6 address, I should have one of these bullets here for each digit of the IPv6 address, right? So just to make, let's say, if I have an address that started with 2000, for example, just to make it easier, we could say that here we have the 2, 0, 0, and 0, okay? Usually what you do is you ask for the full name corresponding to the address. So ip6.arpa, point 2, point 0, point blah, 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 until you get the whole IPv6 address. But what's really cool, and something that was published only a few years ago, is that you don't need to ask for the full IPv6 address space. And you can do this. I can start, let's say that I wanted to scan, let's say, the full IPv6 internet, okay? The full IPv6 internet. I could do this. First of all, I just carry for 0.ip6.arpa, okay? Not the full IPv6 address, just one digit of the IPv6 address, okay? There are two possible options. One is NX domain. This is like DNS response codes. The other one is no error. When you receive an NX domain, this means that there are no domain names hanging from that part of the tree. So if I ask for 0.ip6.arpa and I get an NX domain, this means, look, there are no reverse records for any address that starts with 0. So there are no domain names for 0.0. Blah, blah, not for 0.1 or so on. Now, that gives you this idea. Let's say that I ask for 0.ip6.arpa. I get an NX domain. Does it make sense to go further in that part of the tree? No, because it's empty. What can I do next? I put the 1.ip6.arpa. If the response is NX domain, that part of the tree is empty. Let's say I ask for 2ip6.arpa, and I get a no error. No error means, well, there are names for that part. I don't know where. So you walk the whole space as a tree. So by looking digit by digit, you know if below that digit there are domain names or not. And given, an IPv6 prefix, it's easier to walk and find all of the reverse DNS names. Let's see if I find it. DNS revenue. Clear. Six. Yeah, okay. Okay. So what I'm doing is, first of all, I mean, obviously I know that these people have a lot of things published, right? So I have this prefix here that the people from RIPE use for, at least their website. So now, whoops, clear. So I'm going to do 8.8.8. So I could do like this. It's 3248. So I'm scanning a /48 network. It's even bigger than a /64. Okay? Whoops. Yeah. And then in this one, my local node, it's a clear. Okay. So DNS 11 says. Ah. Okay. Um, these guys updated that. Let's do 28, 64. No. So let's dig. There you go. Mesh 28. Wait, maybe it's the server. Jesus. There you go. Well, I mean, obviously here, this is the one that I did for RIPE, okay? That I was running on a different console. This tool, I mean, since you are sending a lot of UDP-based queries, you know, UDP doesn't have flow control at all. So you have to be careful about the rate at which you send the packets. So this tool essentially measures when, you know, it seems that packets are being discarded. And for example, here, it's telling you, you know, packet loss, so we are increasing the timeout. But look at the numbers. So it got a lot of domains, actually a lot of addresses belonging to that prefix. But what is important here is that it didn't really do an address scan. So it's not that we are proving the addresses. We are learning the addresses because they have reverse mappings, okay? Let's put things this way. If the network administrator wouldn't have configured reverse mappings, we wouldn't have been able to learn all this. Typically, the only systems that really need reverse mappings are SMTP servers, because if not, the other SMTP servers think that you are a spammer. But other than that, you can have a router without reverse mappings, or even a web server, doesn't matter. Now it's it's interesting because some of them like let's say this one. The other time I had run the same thing. This looks like a database or something, right? I mean, it could be, or maybe it couldn't be, but you are getting a lot of IPv6 addresses, and not just that, you are also getting information that's kind of like descriptive of what that address is supposed to be doing. This is, for me, is extremely powerful. I did try with other ones, like there was this I don't even know, like I think it's an educational network in Slovenia called Arnes. I mean, I tried because I know these people, so they were in the training and they said, well, we want to try what we are doing, and you got like 300 systems, similar like that, with very descriptive names and so on. So that's quite cool. Well, this is Arnes, the one that I was trying to, do the same thing, but wasn't getting the responses. I don't know if there was a problem with the DNS server, or maybe they just removed the, the reverse mappings. But you get, file sender, DNSSEC. You see that they are kind of like very descriptive, the names of what those devices are supposed to be doing. And again, /56. We are scanning something even bigger than a 64. Obviously, again, it's not that we're going through all of the possible, we are not pinging the addresses, so to speak. We are walking the address space as a tree. Doesn't matter. And this is last one, two slides, or no more than 2 or 3, that essentially, I mean, it doesn't contain many things that are really practical, but tries to just, let's say, point in a direction. Like, let's say, if you want to spend some time playing or let's say, expanding tools that we currently don't have, that this might give you an idea. You know, as you know, the possibility to do address scans is, let's say, removed or mitigated, because I told you that there are improvements at the ITF. People are, trying to replace the predictable addresses with ones that are random and so on. Obviously, we will need alternative techniques, like the DNS one, for example. We cannot scan a /56 with ping, but with the DNS, that was great. Now, things that might be useful, like there are many applications that leak information about IP addresses in the protocol itself. Like, for example, torrent. You need in torrent like the peers that you could connect to. If you were to build a tool that implements the BitTorrent protocol and gets the addresses from there, you might be able to get the IPv6 address of clients that are just connected to torrent, that they are serving torrents in a different way. Applications that leak information, but this is just one example. It's not that this one is important. This is just one example. Even email. You say, for example, you know that you want to attack a guy, and you say, well what's his email address? No, not his email address, what's his IP address? Because, his address is not predictable, and blah, 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 blah. The guy, maybe he sent you an email address, an email message. You got the address in the header. It's not something that you usually look at, because you look at the, source and destination email addresses, but you look at the headers, and you see that, there's additional information that you could employ. There's email. Email is, an example that, contains a lot of that. But there are other protocols to explore. This is something for which we don't have tools. Like, I don't know I didn't even think about how to build the tool or what are the features that they should support. But, one for, finding clients that are, connected to torrent could be cool. But obviously, to implement the tool, you should need the protocol spec, so it takes the time and effort. PDBD. So getting to the final slide, or trying to summarize everything that we've seen today. So essentially, when you look at the IPv6 addressing architecture, there are a bunch of things that change. Mostly the fact that the address space is much larger. So you have to forget about brute force scans, because the networks are so big that if you want to try every possible address, it's not doable. And there have been improvements both on the attack side and on the defense side. For example, first of all, I published the attack tool, like the scanner. But then I published an RFC to actually mitigate that. So there's like everything. Like there's like a competition, if you want, like from the attack side and the defense side. I would say that over time, when it comes to probably servers and routers, probably their addresses are still going to be predictable, because you are going to use manual configuration for them, like web servers, routers, and so on. But when it comes to clients, I think that we are moving in a direction in which the addresses are going to be randomized. So if you want to learn, let's say, about client addresses to spread a worm or something like that, you should probably evaluate other techniques, like the DNS one that we talked about, anything. Other stuff. As address scanning becomes less attractive, at least for some nodes, obviously you from the point of view of the attacker, have to evaluate, alternative means to get the same information or similar information. In the IPv4 world, typically, the address scans work quite well, or at least for some target networks, that you can get most of the information by just sweeping the the entire address space. With B6, that's not possible. In the case of some nodes that use predictable addresses, like servers and routers, you might be able to do that not with brute force, but with a targeted scan, like just trying to find addresses of specific pattern. With clients, we're moving in a direction again that the address scans are not going to be feasible for finding random clients. So alternative techniques will have to be developed. And probably like a final comment on this is that IPv6 is still a moving target. Like if you go back maybe 3 years, even when it comes to the stuff that I did myself, I had produced a scanning tool, which allowed for the scan attacks to be performed, but I hadn't done anything to try to mitigate them. Now you have both sides moving. So you have implementations that are using random addresses, mitigating those attacks. So it's still, in many different aspects, it's something that is still moving. I don't know if there are any questions. Yes. That's actually I'm probably not going to publish that like this week or next week because I'm traveling, but that's what I have in the pipeline for the scanning tool. Like something to do like massive address scans attacks for IPv6. So you are asking if you have something to do to scan a lot of addresses like you have in IPv4. Well, that's something that I'm implementing, but not yet published. So, this year is going to happen. I don't know if it's next month, in 2 months, or 3 months, but it's going to be published this year. Yeah. Obviously, you can, if you see me here, if you want to ask a question, feel free to do so. That's my email address. Again, if you have a question, feel free to ask whatever. If I know the answer, I'll try to provide it. And there is a mailing list that is focused on IPv6 hacking stuff. The mailing list is quite cool in the sense that you get on the same list both security people, operators, and people that work in internet standards. Okay? Doesn't mean that everyone, participates actively. And even it's funny because obviously I administrate the list, so I'm able to look at the email addresses, and you get like, funny addresses like, Department of Defense or here and there. That's, obviously I don't share that because it's private, but you have quite, an interesting group of people subscribe. And for example, the author of the other toolkit, most of the people that are working actively in IPv6 security, I say all of the ones that I know of are subscribed to the list. So that's interesting. Obviously, if you ask me a question, I will respond it. But let's say if you want to have more than one answer to contrast the answers, maybe I might be wrong. That's a good place to, to ask questions, because if we have conflicting answers, you will see the discussion in there. So it's quite useful. Okay. So thank you, and if again emails, welcome.